Suppose you wake into a world whose rules are exquisitely consistent, whose numbers hum with structure, and whose history is a raucous parade of creativity and catastrophe. You learn physics, and it largely holds. You build computers that can model small patches of reality with eerie fidelity. You watch your species wire a planet, then hurl metal toward other worlds. Along the way, a thought keeps resurfacing. What if the solidity of this whole affair is conditional? Not fake, exactly, just conditional. What if, behind the sensible regularities of your experience, there is another layer? A civilization with technology millions of years beyond yours, running an experiment or a game in which your world is the level set. The NPCs are you and me, and the point of the exercise is to see what intelligence does under pressure. That is the extraterrestrial simulation hypothesis, ESH, in its specific, alien video game styling. It's a cousin of Nick Bostrom's famous simulation argument, which, in compressed form, says that at least one of the following must be true. Civilizations don't reach post-human tech. They reach it, but don't run lots of ancestor sims. Or, if they do run lots of sims, most minds like ours are simulated rather than biological. ESH keeps the computational skeleton, but swaps in an explicit operator, not our future descendants, but non-human, non-terrestrial agents, aliens, who built the sim for their own reasons. It also adopts a practical lens, not, are we in a perfect platonic emulation, but are we inside a bounded, resource-managed, purpose-built environment whose design trade-offs rhyme with game engines and lab experiments? Immediately, two clarifications matter. First, simulation does not imply illusion in the pejorative sense. If you are hit by a bus, you are injured. If you love, you are changed. If a supernova erupts in a galaxy, your telescopes can see. It can fry atmospheres and seed worlds with heavy elements. A simulated world is a rule-instantiated world. Inside it, the rules are reality. Second, video game is an analogy, not a claim that there's literally a cosmic GPU drawing polygons with ragdoll physics. The analogy invites us to think in terms of constraints, render budgets, latency, consistency, and aims, what behaviors are being elicited and measured, and to ask what this framing predicts that plain vanilla cosmology does not. Why propose ESH at all? Three motivations recur. One is explanatory, certain features of the universe, its apparent fine-tuning for complex chemistry, the way quantum mechanics only yields definite outcomes when measured, the deep compressibility of physical law into compact equations, feel like the hallmarks of a system designed to balance richness with manageability. Another is sociological. Intelligent species, as far as we know from a sample of one, create simulated environments for curiosity, training, storytelling, and play. If simulation is a generic capability of intelligence, then in a big, old universe, you should expect sims to be common artifacts. The third is methodological. ESH can be formulated in ways that generate falsifiable predictions, or, at minimum, sharp constraints on what would count as evidence. That makes it a candidate for scientific curiosity rather than pure metaphysics, provided we're careful. The lab rats angle raises the stakes because it adds intention. If aliens are running us to study the emergence of cooperation, the dynamics of technological risk, or the trajectory of planetary stewardship under resource constraints, then history is not only a narrative, but also a dataset. Plagues, cold wars, fossil fuel abundance, asteroid near misses, these become not merely accidents, but potential A/B tests. Most of those tests would be subtle. You neither need nor want overt miracles. You want boundary conditions and distributions that elicit behaviors. The operators of such a sim, if they exist, would be statisticians and designers more than deities. Still, extraordinary claims demand extraordinary care. ESH is not supported by direct evidence. Many popular glitch stories, Mandela effect memories, déjà vu spikes, matrix birds, flying weirdly, are excellent psychology and poor physics. Our brains are compression machines riddled with shortcuts and biases. In a noisy world, coincidences are inevitable and narratives stick. Likewise, speculative claims that the universe encodes error-correcting codes, or that the cosmic microwave background contains messages collapse under scrutiny, or are misreadings of subtler math. If we adopt the alien video game frame, it should be because it helps us reason more clearly, not because it gratifies our appetite for mystery. Features. In game engines, nothing is rendered without a reason. You stream textures only when the camera needs them. You cap physics updates to a tick rate. You offload repeated structure to procedural generation. If physics were an engine, you would expect analogous economies. Locality, no action at a distance. Finite propagation speeds, light cone, causality. Quantization, only discrete states to compute. Symmetries, reuse code aggressively. And a deep preference for compressible regularities, laws. You would also expect stochasticity, where global calculation would be too expensive, which makes quantum randomness feel less magical and more practical. None of this proves anything, but it gives a program for mapping engine constraints to physical law and asking where the analogy breaks. Second, a way to reframe existential puzzles. The Fermi paradox, where is everybody, can be softened if we're not looking at base reality. If we inhabit a sim that suppresses direct contact, either for experimental control or because NPCs who meet their designers derail the study, then the silence is a feature. Likewise, why is the universe so big becomes a question about scope. If the study's dependent variables need billions of independent trials for complex life to emerge, a roomy parameter space is a design goal, not waste. Even the apparent indifference of physics to our hopes can be reframed. A good experiment avoids demand characteristics. Third, a cautious ethics. If we are lab animals in a super sophisticated enclosure, then our moral circle includes not only one another and other Earth life, but also any simulated minds we create. If nested simulation is possible, sims inside sims, then our choices may spawn whole populations whose lives are as real to them as ours are to us. The lab rat metaphor, uncomfortable as it is, underscores obligations to minimize suffering and to treat agents as ends in themselves, even if the metaverse above us is indifferent. Ironically, an alien-run sim can sharpen humanism. The rest of this script works like a careful dungeon crawl through the metaphor. We'll check computational plausibility. Could anyone run this? Inventory putative signatures. What would we even look for? Tor motivations. Why would anyone care? And confront both the epistemic hazards and the practical ethics. At each step, we'll keep two guardrails. We won't pretend weak evidence is strong, and we won't cash out meaning in cynicism. Whether base or simulated, lived experience retains its gravitas. The bus still hurts, love still changes you, responsibility still binds. Before we argue over motives or ethics, we have to ask the basic feasibility question. Could any civilization, ours, our descendants, or aliens, actually run a simulation at the scale and fidelity of our observed universe? The answer depends on two linked considerations: how much reality you need to compute to deliver experiences like ours, and how much computation a very advanced civilization could plausibly marshal. If the first is astronomical and the second is meager, ESH is dead on arrival. If the first can be made efficient and the second can be grown prodigious, it stays in play. Start with the demand side, the cost of appearing real to embedded observers. The naive approach is hopeless, explicitly calculating every particle interaction in a Hubble volume at Planck time steps would annihilate any imaginable computer. But that's not how good simulators, or nature, work. Three economies rescue the idea. The first economy is locality plus sparsity. You only need high fidelity detail, where it causally matters to an observer's next observations. Your brain doesn't render every atom in the Andromeda galaxy. It renders a few million pixels of a telescope image and the statistical behavior of photons that reach your detectors. A sim can exploit the same trick, store global structure as compressed rules, field equations, boundary conditions, stochastic processes, and only instantiate microstates when observations force disambiguation. This is, intriguingly, close to how quantum mechanics behaves. Systems evolve according to compact wave equations until measurements yield definite outcomes sampled from probabilities. Whether or not quantum theory is literally an on-demand rendering system, it has that vibe. The second economy is symmetry and compression. Physics is drenched in symmetries, translation, rotation, gauge invariances that let you reuse the same computations everywhere and everywhen. The code base is tiny relative to the content. When you discover that the laws that govern hydrogen spectra in stars also govern fluorescent bulbs and quasar absorption lines, you're witnessing compression ratios a software engineer would envy. The sim designer only pays for the law once, the universe pays it off endlessly. The third economy is multi-scale modeling. Many macroscopic phenomena are insensitive to micro details. You can model airflow over a wing with continuum equations without tracking each molecule. You can simulate climate with grid cells and parameterizations. A sim that picks the right effective theories at each scale avoids wasting cycles on precision no observer could access. If you're worried about observer hacking, clever physicists building instruments to probe the microstructure, you can allocate more compute adaptively in regions where measurement resolution grows. That's akin to adaptive mesh refinement in computational fluid dynamics, and it mirrors how game engines increase detail where the camera lingers. Now, the supply side. How much computation could aliens have? Kardashev's scale classifies civilizations by energy use. Type 1 harnesses a planet's output approximately 10 to the power of 16 to 10 to the power of 17 watts. Type 2 are stars, 10 to the power of 26 watts. Type 3 are galaxies, 10 to the power of 36 watts. Wrap a star in a swarm of energy collectors, a Dyson swarm, and you get a matryoshka brain, a layered set of computing shells sipping nearly the full solar luminosity. Converting that energy into operations bumps hard into physics limits, but those limits are high. Landauer's principle says there's a minimum energy cost to irreversibly erase a bit, proportional to temperature, but if your computers run cold in deep space, the cost plummets. The Margolis-Levitin-bound caps how fast a quantum system can evolve per unit energy. Again, at stellar power, the ceiling is lofty. Even conservative estimates yield operation counts that dwarf anything we can do. Importantly, you don't need to emulate the entire cosmos at maximum fidelity. You need enough to produce consistent observations for all observers who will ever make them. The number of observers and the bandwidth of their experiences matters more than volume. A human brain runs maybe 10 to the power of 14 to 10 to the power of 17 operations per second, depending on how you count. A planet of billions of such agents is computationally heavy, but not galactic heavy compared to stellar resources. Add in ecosystems, weather, and the physics that supports them, and the bill is large but not obviously intractable for star-scale sieves, especially if the sim is cleverly sparse and adaptive. What about nested simulations? Sims inside sims. That's an infamous regress. Each layer taxes the next, but it doesn't have to explode if each level only grants its denizens a fraction of base resources. If the top-level sieve has 1 million compute units, it could run 100 worlds each with 10,000 units. Each of those could run a handful of inner worlds, and so on, with diminishing fidelity and scope. That structure is familiar in cloud computing quotas and virtualization today. The practical upshot: nested sims are plausible up to a depth where fidelity becomes too thin for complex life. If we ever manage to run convincing civilizations ourselves, that fact would update ESH's prior upward. If we can do it, so could someone ahead of us. Feasibility isn't only about raw ops, it's also about reliability and design. A long-running sim must avoid cascading errors and resource leaks. It needs checkpointing, saving state, redundancy, so cosmic rays in base reality don't scramble your universe, and mechanisms for graceful degradation. Local glitches don't crash the whole. It probably enforces conservation laws and know-there-ish symmetries, not just because the math is pretty, but because invariants guard consistency. It may sandbox high-risk experiments. If inhabitants start building planet-busting devices, you don't want their antics to destabilize your compute substrate. In our world, the fact that physics is so stubbornly stable, that violations of conservation are vanishingly rare, reads as both a deep feature of reality and, on the sim reading, as a good engineering choice. Could we detect the compute substrate? A playful proposal by Bean and colleagues suggested that if the universe were computed on a lattice with finite spacing, ultra-high-energy cosmic rays might reveal anisotropies, preferred directions, due to the grid. That's a neat idea, but real lattice spacings could be so fine and the engine so clever that any signal is swamped. Similarly, ideas about finding error-correcting codes in the fabric of reality are often overinterpreted. Yes, quantum error correction is a fruitful way to think about spacetime in certain theories, but that's not the same as spotting a watermark that says, made by zeta reticulans, third shift. Evidence here will be indirect, statistical, and forever contestable. Finally, there's the question of purpose, because it feeds back into feasibility. If the goal is to study the emergence of cooperative intelligence on a temperate planet, you do not need to simulate galaxies in loving detail, except as boundary conditions that yield heavy elements and stable star life cycles. If the goal is to train agents for open-ended problem-solving, you might vary planetary histories and biospheres across many runs to explore the space of possible civilizations. If it's entertainment, scope and spectacle matter. If it's education, clarity and manipulability matter. If it's pure science, coverage and replicability matter. Each purpose sets a compute budget and a fidelity target. The phrase alien video game compresses many motives, but all of them are compatible with a universe that feels, from the inside, both lawful and lush. So, on balance, ESH clears the feasibility bar in principle. That does not make it likely, let alone true. It means only that when you draw the supply and demand curves for computation and fidelity, they plausibly cross in a region reachable by civilizations far older and richer than ours. If you treat the universe as a purpose-built environment, the way a game designer treats a level, then the most striking thing about our world is not its objects, but its rules. The rules are stable, universal, and astonishingly compressible, as if a small set of invariants and update laws are being applied everywhere with perfect discipline. That is precisely how you would build a scalable world. You would pick a compact rulebook, insist that it be local so that updates can be computed in parallel, and guard it with symmetries so that the same code applies at every location and orientation. Seen through this lens, many of the curiosities we file under physics start to look like good engineering practices. Begin with the speed of light as a hard limit. In ordinary programming, when you need to synchronize a distributed system, you either pay in global locks, which destroy scalability, or you insist that information cannot propagate faster than the time it takes to signal along the network. Special relativity reads like a victory for the latter approach. If no causal influence outruns a finite signal speed, you can update the universe in a massively parallel way without ever having to halt everything to reconcile state. Light cones become not just geometric ornaments, but the concurrency limits of reality. The fact that this limit is invariant for all observers, no matter how they move, amounts to saying the network guarantees a maximum bandwidth per tick that no local frame can cheat. In an engine, that's how you avoid paradoxical race conditions. In physics, it is how you avoid causal loops. Next, locality. Interactions in our world are short-ranged in the information sense. The equations that tell a field or particle how to evolve depend only on values in its immediate neighborhood. That's perfect for tiling the universe into independently updatable chunks, cells for a lattice, simplices for a causal set, patches for a finite element scheme, or neighborhoods for event-driven updates. Long-range effects always mediate through fields that themselves propagate locally. Gravity, which pulls over vast distances, is described not as action at a distance, but as curvature in a local geometry. To a designer, this is the difference between a naive n-body algorithm that scales quadratically and a fast multipole or grid-based solver that scales linearly, or n log n. Locality is compute economical. Quantization has the same flavor. If you allow arbitrary real-valued state at every degree of freedom, you are committing your engine to track infinite precision. That's a recipe for numerical instability. A discrete spectrum, energy in quanta, angular momentum in integer or half-integer steps, spin with two or a handful of orientations, keeps the state space countable and the bookkeeping robust, while still offering staggering richness at macroscopic scales. The Planck constant functions like a global resolution setting, fine enough that classical-looking behavior emerges for large aggregates, coarse enough that the micro-world cannot explode into pathological infinities. In fact, one of the great gifts of quantization is stability. Atoms don't radiate away their energy on a smooth slide to zero because the ladder has rungs. In a simulation mindset, that is exactly the sort of guardrail you would implement to keep complex structures from disintegrating. Symmetry is the unmatched compression engine. In field theory, you can write a shockingly short Lagrangian that yields the lion's share of known particle physics because the real creative act is choosing what symmetries you will not allow your equations to violate. Noether's theorem then hands you conservation laws as invariants of the update loop. Time translation, symmetry buys energy conservation. Space translation symmetry buys momentum conservation. Rotational symmetry buys angular momentum conservation. And so on. In code, invariants like these are not just elegant, they are sanity checks that prevent drift. A simulation with exact symmetries inherits exact conservation, which protects consistency over mind-bending runtimes. Lorentz invariance does double duty. Physically, it tells us there is no preferred rest frame. The laws look identical to all inertial observers. Computationally, it means there is no privileged update grid that would peek through the physics as a directional bias. If your engine chose a naive cubic lattice with a coarse spacing, ultra-energetic phenomena might feel the anisotropy and betray the underlying scaffolding. The fact that we have not found that sort of directionality at accessible energies implies either that the scaffolding spacing is fantastically fine, or that the substrate uses clever tricks, random lattices, causal sets, or algebraic approaches where geometry is emergent, to avoid imprinting a grid signature. A well-designed engine would do the latter, because symmetry breaking where you don't intend it becomes a debugging nightmare. Time itself asks for care. Many game engines update in ticks, discrete frames in which physics advances and render states are committed. But ticks need not be global. Asynchronous event-driven simulations advance local regions when and only when something happens that demands computation. That picture rhymes with the quantum notion that unmeasured systems coast on smooth unitary evolution until interactions trigger decoherence and definite outcomes. It also fits the thermodynamic arrow. Entropy gives you a statistical notion of time's direction without requiring a universal master clock. A designer would seize on such constructions because global clocks are brittle. Local clocks, proper time along world lines, keep the whole show flexible and scalable. Randomness is often where people smell the supernatural, but in engineering it can smell like thrift. If you attempt to calculate the exact, deterministic microstate evolution of a turbulent fluid, you will waste cycles producing digits no observer could ever access. Instead, you sample from well-tested distributions that reproduce the correct statistics. Quantum mechanics could be doing something analogous, and indeed the formalism is statistical at its core. Whether the randomness is fundamental or a cryptographic-grade pseudo-random number generator in the substrate is one of those questions that likely stays philosophical, because a good generator deliberately defeats finite observers. Either way, randomness deployed at the right seams tames compute without flattening richness. Zoom out to the structure of effective theories. One of the top-tier ideas of 20th century physics is the renormalization group. As you look at the world at different scales, different variables become the right descriptors. and many micro details wash out. Critical phenomena, like water boiling, magnets losing their magnetization, or universes inflating, exhibit universal behavior that does not care about molecular specifics. That is the algorithmic heart of level of detail management. You build a system whose micro rules deliver, at larger scales, simple, near-scale invariant patterns, so you do not have to manage every micro decision to predict macro behavior. If we were authoring a simulation with hopes of birthing chemistry, biology, and culture, we would kill for a renormalization group. Information bounds add an unmistakable engineering accent. The idea that there is a finite maximum information content for a bounded region, the sort of thing captured in the Bekenstein bound and the entropy of black holes, sounds like a memory budget. The holographic principle is more striking still. The maximum information in a volume scales with its surface area, as if the engine stores reality on the boundary and computes the interior on demand. In theoretical physics, this is not a gimmick, but a profound duality between descriptions. From the sim perspective, it is also a fantastically efficient storage discipline. Boundaries are cheaper to maintain than volumes, especially when observers mostly interact with fluxes crossing surfaces. Even the messiness of the real world can look like planned complexity. The cosmic web of galaxies, filaments, and voids resembles the output of simple rules iterated under noise and gravity. Planetary systems with resonances speak to emergent order from local interactions. Life and mind appear as structures perched near criticality, poised between order and chaos, where diversity and adaptability flourish. If you were tuning a game for interesting play, you would gravitate to that edge. Too much order, and nothing surprising happens. Too much chaos, and nothing endures. Physics seems to have found this knife-edge sweet spot across scales. Still, analogies are not arguments. For every feature that looks like an engine constraint, there is a sober base reality explanation. The speed of light is not an arbitrary throttle, but part of spacetime's geometry. Quantization arises from the structure of Hilbert spaces, not necessarily from desire to keep integers. Symmetries are empirically discovered and mathematically entailed by deeper principles. They are not proof of a coder's penchant for reusable modules. The holographic principle emerges in certain theories of gravity and quantum fields. It is not primarily a compression hack. If you lean too hard on the metaphor, you risk reading your preferences into nature. The right way to harvest the metaphor is to ask what it predicts that bare physics would not bother to phrase. It predicts an extreme aversion to global constraints that would demand cross-cosmic coordination in a single step. It predicts computation-friendly locality and update rules. It predicts that when observers try to force the world into global synchrony, or to exploit non-local correlations for signaling, the rules will bite back, as they do in no-signaling theorems for quantum entanglement. It predicts that when the cost of maintaining detail exceeds any possible observer's access to that detail, the world will answer with stochasticity and effective theories rather than infinite exactitude. And it predicts that symmetries and invariants will be the sacred cows because they make long-run consistency possible. There is also an unexpected place the metaphor helps: error handling. Real-world numerics suffer from rounding, truncation, and chaos. If the substrate must preserve coherence over cosmological durations, it needs redundancy. The observation that quantum error-correcting codes provide a language for space-time structure, in some approaches, hints at a world where the fundamental fabric is designed to survive noise. Whether or not that reflects a sim's priorities, it certainly matches an engineer's. In a universe that can host thinking beings, you cannot afford catastrophic bit rot. Finally, constants and tunings. A designer of a world that supports complex chemistry would tune a small set of dials to land in a regime with stable nuclei, long-lived stars, and diverse bonding. Our universe appears to sit in such a regime. That fact alone does not discriminate between selection effects in a multiverse, providential design, or an alien sim targeting interesting runs. What the design lens does do is reframe the question as an optimization problem. Given constraints, compute, time, temperature, and objectives, emergent complexity, agent training, planet-scale social dynamics, what region of parameter space would you choose? A surprising number of our constants and structures look as if they live in those regions. That coincidence is jarring or inspiring depending on your taste, but it is at least a systematic way to think about why the rules are as tight, local, symmetric, and quantized as they are. In the end, game design logic as physics is not a claim that someone is flipping switches behind the curtain every 16 milliseconds. It is a disciplined analogy that takes seriously the computational cost of a richly populated, law-governed world, and notes how our physics seems preternaturally aligned with what such a world would require. You can remain a realist about fields and particles and still notice that the rulebook reads like an object lesson in scalable design. If we grant that the alien video game frame is coherent and even computationally plausible, the honest next question is brutal. What would count as evidence? Not vibes or poetry, but observations that should move a careful Bayesian from cute analogy toward live hypothesis. The sobering answer is that most alleged signs evaporate under scrutiny, and that the class of evidence we can reasonably hope to see will be statistical, indirect, and permanently contestable. That does not make the inquiry pointless. It does force us to reject easy answers and to define, ahead of time, what would change our minds. The lowest quality evidence is anecdote, glitch stories, déjà vu spikes, memories that diverge from the historical record, uncanny coincidences. Human cognition is a superb, pattern-seeking, compression-loving engine that aggressively fills gaps, smooths contradictions, and weaves narratives. In a world with billions of people generating trillions of experiences, extreme coincidences are not just possible, they are guaranteed. The social internet then amplifies the most arresting tales, and a selection-biased feed makes the improbable feel routine. None of this is a knock on lived experience. It is a caution that subjective strangeness is a poor detector for substrate truth. If we are to take ESH seriously, we have to put personal weirdness in a quarantine jar and turn to public, repeatable measurements. A step up are claims of coded messages in nature, prime number patterns in the cosmic microwave background, alignments of low-order multipoles in the sky, strange clustering in fast radio bursts, or a one-off radio event like the historic WOW signal. In each case, the most sober assessments point to either mundane origins, instrumental systematics, or the look elsewhere effect, where you only report the surprising subset of many possible summaries. The cosmos is large and noisy. If you compute 1 million different statistics on it, a few will look remarkable by chance. The cure is pre-registration and replication. Specify, before looking, which statistics you will compute and what thresholds would count as significant. Then test those statistics on independent data. Absent that discipline, pattern mining the sky will produce stories faster than reality produces causes. What about digital scars, signatures that our world is computed on a lattice or within a finite precision arithmetic? Proposals here are charmingly concrete. Maybe ultra-high energy cosmic rays will betray a preferred direction because the underlying grid is anisotropic, or maybe high-frequency gamma rays from distant explosions will smear or arrive out of order if there is a minimum time step. Experiments have hunted for these effects in various guises, and so far have only produced tighter bounds on how Lorentz invariant and isotropic the world appears at accessible energies. That is exactly what a careful sim would aim for. If there is a grid, its spacing and update rules are arranged so that no realistic experiment sees the joints. Calling this evidence against ESH is too strong. It is, at best, evidence against naive implementations. Variation in fundamental constants is another tempting avenue. If the universe were receiving hot patches, or if its underlying parameters drift as the engine is retuned, we might catch tiny changes in the fine structure constant, the electron-proton mass ratio, or the strength of gravity across time or space. Astronomers and laboratory physicists have looked with exquisite sensitivity, comparing atomic clocks, combing spectra from ancient light, and probing natural fission reactors in the geologic past. The constraints are tight. If there is drift, it is small enough that it hides beneath our current detection. Again, that is consistent with both base reality and with a well-behaved long-run sim. It nudges no needle. Information theoretic limits could be misread as fingerprints. The existence of bounds on information density and processing, the holographic scaling of entropy for gravitational horizons, the deep connections between geometry and entanglement. These might feel like peeks behind the curtain, as if we have reverse engineered the storage budget and error correction strategy of the substrate. But those same facts have natural homes in base reality theories. They are powerful constraints on any possible world that hosts quantum fields and gravity, not leaked documentation from a cosmic dev kit. Their evidential weight for ESH is neutral at best. A more dangerous category is interventionism, the hope that the operators will respond if we address them. Some suggest transmitting messages crafted to be legible to a meta-observer, inserting moral arguments or cleverly compressed proofs into mathematics or skyglyphs, and then monitoring for improbable coincidences that would indicate a reply. The ethical and epistemic problems here are acute. Ethically, you are attempting to manipulate beings who may have placed us under control conditions. Epistemically, any anomaly you find is nearly impossible to distinguish from noise without pre-registered criteria, and the risk of motivated reasoning is extreme. Worse, a culture that believes it can appeal to the operators for favors is ripe for fanaticism and exploitation. For our purposes, talking to the devs belongs in the category of ideas to analyze, not to practice lightly. One test sometimes floated is to push physics toward algorithmic hardness and watch for lag. The thought is simple. If the substrate computes outcomes, then experiments whose outcomes are costly to compute, say, contrived many-body quantum interference with high circuit complexity, might show longer rendering times, higher error rates, or correlated failures. Design such experiments carefully, increase complexity past certain thresholds, and look for a performance cliff that shouldn't exist in base reality. There are two problems. First, real laboratories already suffer from scaling cliffs due to decoherence, noise, and control errors. Separating a hypothetical substrate lag from mundane engineering limits is brutally hard. Second, a good substrate is not obliged to compute by brute force. It can exploit structure and clever sampling, just as we do, making the relationship between our algorithmic hardness and its cost opaque. The idea is intriguing enough to merit formalization, but any positive hint would demand paranoid scrutiny. Another seductive line is to hunt for global coordination phenomena that shouldn't be available to local laws. If the world were secretly stitched together by a scheduler, you might find inexplicable correlations across space-like separations beyond what quantum mechanics allows. So far, every time we have tightened tests of locality and freedom of choice loopholes in Bell-type experiments, quantum theory has held. We get non-local correlations, yes, but never signal-bearing ones. We get weirdness, but not the wrong kind. An operator determined to keep no signaling safe would celebrate that result, and a base reality built on quantum fields demands it. The most honest route is a research program that refuses to privilege ESH while still using it to generate sharp, risky predictions. Define classes of anomaly, Lorentz violation at extreme energies, time dependence in constants, statistically significant departures from quantum randomness in carefully isolated systems, systematic failures of effective theories exactly at the point their computational cost spikes, and then build experiments designed to detect them with pre-registered analyses. Publish the protocols in advance, share data openly, recruit adversarial collaborators to try to kill the results and resist the internet's appetite for premature narratives. If nothing turns up after a decade of such work, that is not a disproof, but an update. The posterior shrinks. If something sturdy turns up, we have learned something deep, whether or not we attribute it to an alien substrate. Equally important is to name the kinds of findings that do not count. a pleasant coincidence that benefits you personally, a cultural vibe that things feel scripted, an isolated statistical blip found after multiple peaks at a data set, a pattern that evaporates under different binning or filters, an experiment that fails to replicate outside one lab, a claim that binds its credibility to the charisma of its advocate. None of these are evidence. They are invitations to curiosity, not to belief. Because ESH is an idea that can intoxicate, clarity about evidential standards is a moral duty. What would success look like in principle? The gold standard would be a robust, repeatable, pre-registered result that violates a bedrock symmetry or conservation law in a regime where no known extension of physics expects it, accompanied by a pattern across related phenomena that points to a single, compact, predictive modification of the rules, a modification that looks suspiciously like an implementation detail. Even then, calling that evidence of aliens would be hubris. It would be evidence of new physics. Only if that new physics bore a specific signature of design intent, say, an energy-dependent anisotropy that looks like a computable stencil, or a boundary-encoded pattern that carries unambiguous high-level information, would the needle move decisively toward ESH. That bar is very high by design, so we arrive at a sober balance. The world is weird enough to inspire the simulation lens, and disciplined enough to resist its cheap confirmations. Our task, if we are serious, is to carry two thoughts at once. That ESH is a live possibility in a very large space of possibilities, and that almost everything we can check will likely return nulls or ambiguities. The right posture is curious, methodical, and allergic to fantasy. We can keep looking without letting the looking deform our ethics or our grip on reality. If we are lab rats in an alien video game, then the standards of evidence we hold ourselves to are part of the test. Let's try to pass it. The Fermi paradox sounds simple until you stare at it long enough that it starts staring back. Given a galaxy with something like 100 billion stars, many older than the Sun, given planetary systems that look more common than not, and given evolutionary timescales that comfortably exceed the span from the first replicators on Earth to radio telescopes, where is everybody? In the simulation frame, the silence is not a raw fact about base reality, it's a contingent property of our instance. We might live in a run where the operators, whether scientists, educators, artists, or safety engineers, have reasons to keep the sky quiet, the neighbourhood sparse, and our line of sight uncluttered by obvious megastructures. That reframes nearly every classic solution to the paradox as a parameter choice, boundary condition, or policy setting rather than a metaphysical necessity. Start with control of confounds. If your goal is to measure how one planetary civilization handles coordination, risk, and technological growth, the cleanest experiment minimizes off-world influence. Allow early contact, and you entangle variables. Developmental arcs converge. Local incentives warp toward imitation or resistance, and the signal of endogenous cultural evolution gets contaminated by imported ideas and artifacts. A strict no-contact policy, whether implemented as a genuine absence of nearby technological civilizations in this run, or as a filtration layer at the edge of the sim that suppresses inbound and outbound techno-signatures, keeps your dependent variables legible. To denizens, this reads as a mute cosmos. To designers, it looks like good experimental hygiene, then bandwidth and compute. Interstellar conversations among many advanced species are a synchronization nightmare. Cross-cultural semantics, multi-channel protocols, artifact exchange, verification of proofs, escalation to demonstrations of exotic physics, all of that demands high-fidelity modeling across enormous volumes. If the operator's objective is depth over breadth, watch one lineage closely rather than a dozen superficially, then a cheap way to cap computational load is to set initial conditions that produce a wide but empty local bubble. 1,000 light-years of silence keeps the rendering and logging budget focused where the outcomes are, on the single biosphere under study. The effect feels to us like existential solitude. In a lab notebook, it's a resource allocation strategy. Selection effects sit on top. If you are interested in the bottlenecks that winnow intelligent life, ecological fragility, information hazards, institutional failures, runaway technologies, you will keep, or at least extend, runs that hover near those thresholds. Our history looks suspiciously like that kind of edge case, a species that bootstraps global industry quickly enough to steal energy from geologic stores before it learns planetary stewardship, that acquires the ability to alter genomes and climate before it can coordinate on norms, that explores the physics of the very small while struggling with error bars and replication. In a library of runs, these cusp cases are gold because they reveal which norms, institutions, and technical choices stabilize flourishing. The great filter is still a filter, but in the sim lens, you bias your archive toward worlds that press up against it, rather than worlds that sail through it early and zoom off to the stars. Megastructures are the poster child for techno-signatures, and they too bend under this lens. In base reality, Dyson-like energy collectors should glow in the infrared. Galaxy-scale engineering should warp dynamics in ways we can see. Our surveys have not found saturated stellar swarms or galactic realms under obvious management. That might mean they aren't there. It might also mean the renderer does not include them for this run, or the parameter set disincentivizes star harvesting regimes that would look like waste heat seas to our telescopes. A conservation-minded operator might seed a universe where the easiest path for smart species is go inward, virtualize, compress, use colder and subtler energy gradients, so the thermodynamic footprint stays low. In our observational practice, that is functionally indistinguishable from absence. Habitable time waves let the operators tilt the table with astrophysics rather than miracles. Star formation is not uniform over time. Metallicity rises as generations of stars live and die. Sterilizing events like gamma-ray bursts have their own eras and gradients. We could inhabit a patch of the simulation where the present is still relatively early in the local habitable epoch, with many worlds behind us in time, and far enough away that their techno-signatures fall outside our light cone. Or we could be placed near the leading edge of habitability, so that nearby peers simply haven't had time to appear. Both choices are consistent with known physics and with a watch one world develop in relative quiet design brief. The sky we see is generated by rules. The dataset filling those rules can still be curated. SETI expectations change accordingly. In a pure base reality picture, it makes sense to search the radio spectrum, optical bands, and the infrared for deliberate beacons, traffic leakage, or waste heat from industry. In a curated instance, deliberate beacons are either redacted at the boundary or never launched by our neighbors because our draw was sparse to begin with. Traffic leakage never arrives. Waste heat is either non-existent or disguised by parameter choices that push advanced species toward low-footprint energetics. That doesn't make listening pointless. It refines what null results mean. A long, well-conducted null program becomes evidence about the run's scope and policies as much as about the galaxy's base reality ecology. Even where is everybody might be the wrong question if the objective is to see whether we can build everybody here. A training or alignment-motivated operator could be watching whether a single species can expand its circle of concern to include all local minds, human and non-human, without the goad of an alien other. The temptation to conjure extraterrestrial enemies or saviors has been a recurrent political crutch. A mute sky forces us to grow institutions and virtues without that narrative. In game design terms, silence is a difficulty setting that makes coordination and foresight the only path to win states like long-run stability and fair prosperity. Many familiar non-sim answers to the paradox remain live, and the sim lens doesn't dissolve them. Abiogenesis could be rare, multicellularity could be fragile, technological civilizations might self-limit voluntarily, cosmic distances could be a practical deterrent to colonization, even with advanced drives. The simulation framing earns its keep when it explains features those accounts leave untouched, like why rare consistently looks like just quiet enough now for this one world to mature, or why null results persist even as our instruments improve, or why certain windows of possibility, industrial energy abundance, global communications, survivable pandemics, seem to time themselves to maximize stress tests of cooperation. You do not need a cosmic admin to set those dials, but if someone did, the world might look like this. What would we expect to observe under different operator motives? A research-first run should show minimal intervention, consistent physical law, and a clean sky. An education-first run might add staged crises pacing, problems that are solvable but require social learning, appearing in an order that lets institutions scaffold. A conservation-first run might present unusually resilient ecosystems and persistent cultural diversity, with subtle nudges away from monocultures. An entertainment-heavy run might lean into arcs of discovery, reversals, and the uncanny coincidence of crucial inventions with available resources. A safety alignment run would elevate dilemmas where agents face temptation to defect for short-term gains, and where the payoffs for cooperation are real but delayed. The observable signature across all of them is silence toward the outside. The differences show up inside history's texture. Are there costs to taking this seriously? Yes. The sim lens can become a universal solvent that dissolves hard astrophysics into speculative psychology. The way to avoid that is to keep it as a conditional frame, useful where it clarifies, mute where it distracts. The why silence question is one such clarifying zone. Under any motive complex that includes control, curation, or compute thrift, you get a quiet neighborhood with physics that resists exploitably non-local hacks. That means we should expect the paradox to persist as instrumentation improves, because the null is not a failure of search, but a feature of the instance. It also means our energy is better spent on local flourishing and disciplined observation than on desperate sky shouting. There is, ironically, a civic upside to the sim-flavored resolution. If the silence is a condition rather than a verdict, then despair is a category error. The right response is not, we're alone forever, nothing matters, but we have room to grow without interference. What will we do with it? The paradox becomes a mirror. The answer to, where is everybody, is here, and the task is to become the kind of everybody we'd hope to meet, whether the operators ever open the quarantine or not. This is the thread that ties the paradox back to ethics. Whatever the outer story, the inner story is ours to write under constraint, and the absence of neighbors is a radical invitation to get that story right. Test it, but don't break anything, is easy to say, and hard to do when the thing you're testing might be the boundary of reality. The extraterrestrial simulation hypothesis is a minefield of motivated reasoning, social reward for wonder, and epistemic traps disguised as evidence. A credible research program has to do three things at once: squeeze genuine information from experiments even when the headline result is nothing there, insulate itself against self-deception and hype, and refuse methods that gamble with shared risk or dignity on the theory that the operators will catch us if we fall. The path forward is a bundle of discipline, design, and ethics. Discipline begins with pre-commitment. Before you look at any data in a domain where post-hoc storytelling is cheap, anisotropies at extreme energies, tiny drifts in constants, subtle departures from quantum random bit streams, you publish a protocol that nails down what counts as a signal, how you'll process it, what thresholds trigger follow-up, which data sets are for discovery and which are for replication, and what the stopping rules are. In a world overflowing with degrees of freedom, this is the only way to stop the look elsewhere effect from minting miracles out of noise. The point isn't bureaucratic purity, it's to ensure that when you do see something surprising, you know how many shots you took at the target. Design means choosing seams where physics and computation meet in ways that make the sim lens concrete without begging the question. One seam is randomness. If the universe samples outcomes from a truly fundamental distribution, then long bit streams drawn from well-isolated quantum sources should pass algorithmic randomness tests up to the precision we can achieve. If, instead, Randomness is produced by a substrate pseudo-random generator, PRNG, hidden behind physics. There is a sliver of possibility that exquisitely tuned tests could detect structure, subtle bias under certain constraints, unexpected serial correlations, or departures from algorithmic incompressibility in pre-registered assays. You would build ultra-stable photon pair sources, drive Bell-type experiments that use cosmic photons as setting choices to minimize local hidden variable loopholes, and feed the outputs to battery-tested, pre-declared suites of randomness audits. The default expectation is passes with flying colors. The value of the work is tighter confidence bounds and better metrology. If a deviation survives hardware swaps, code audits, and independent replication, then you have something serious. Whether it says sim or new physics is a later question. Another seam is scaling under complexity. Laboratory quantum systems already punish hubris. Noise grows, control falters, and decoherence eats the beautiful interference you wanted. But you can still ask whether error rates, decoherence times, or failure modes track physical complexity in the way our theories predict, or whether they anomalously track algorithmic complexity, circuit depth measured in Kolmogorov-like surrogates, entanglement structure specified by tensor network ranks, or instance hardness under classical simulation. A pre-registered program would vary those algorithmic properties while holding physical knobs flat and watch for systematic cliffs that do not belong in base reality models. The substrate panic myth, overwhelm the renderer and it will lag, is cinematic nonsense. A clever substrate exploits structure like we do, but a genuine, reproducible, complexity-tied deviation would be so weird that even a closed-minded realist would have to learn something new. Symmetry tests live here too. If the rules of our world are the compiled invariants of an efficient engine, some symmetries might be exact by design because they are cheap sanity checks, conservation via Nother. Others might be only as exact as they need to be. High-precision comparisons of atomic clocks hauled through gravitational potentials, ferocious checks on Lorentz invariants using gamma-ray bursts, and ultra-high-energy cosmic rays, CPT tests in particle systems. These are standard physics lines that double as substrate hunts if you phrase them carefully. You never announce code peeking through the grid. You announce, we have evidence of tiny anisotropy at X sigma that conflicts with Y theory under Z assumptions. And only after pounding the result flat do you allow yourself a paragraph about possible implementation detail readings. There is an alluring but perilous category of operator contact experiments. Compose messages designed to be semantically legible across ontologies. Broadcast them through channels you hope an outer layer can monitor. Promise to interpret any subsequent improbable coincidence as acknowledgement and wait. This is epistemically bankrupt unless you do the statistical groundwork that almost nobody does, calculating base rates for coincidences under your exact selection pipeline, pre-registering what counts as acknowledgement versus noise, and arranging for adversarial teams to try to falsify your interpretations. It is also ethically dubious. You create a cultural incentive to seek signs and wonders. You prime publics to see patterns where there are none. You give demagogues a lever. A responsible program treats talk to the devs as out of scope until and unless we've earned the right to ask by building ironclad anomaly catalogues that survive hostility. Communication norms are the scarcest resource. ESH is meme magnetic. Attention rewards certainty over care. So you slow yourself down on purpose. Claims labeled anomaly are embargoed until they pass internal replication. Code and data are public upon release, and independent labs pre-committed to your protocol can try to kill the effect before the press hears about it. You lead with Steelman alternatives. You publish your raw data and your nulls. You prize adversarial collaboration. Proponents and skeptics author the same paper, agree on the thresholds in advance, and co-own the outcome. The goal is not to be first, it is to be right, or, if wrong, to be wrong in ways that teach. Ethics sets red lines. You categorically reject stunts intended to force the operator's hand. That includes world-scale geoengineering gambles without broad consent, transmissions designed to provoke meta-attention, experiments whose only rationale is to try to trip a hypothetical safety interlock and risk arguments that smuggle in divine providence logic. If it's dangerous, they'll stop us. The sim lens never licenses recklessness. If anything, it raises the bar, because your experiment might not only test physics, it might be part of the very variable the outer study is measuring, whether we can govern ourselves under uncertainty. Institution building is part of the method. Imagine a standing consortium, the substrate inference collaboration, that acts more like a clinical trials network than a loose collection of hobbyists. It maintains a public registry of planned tests and analysis choices, coordinates data standards so that negative results can be meta-analyzed, rotates leadership to avoid identity capture, and runs code sharing and hardware swap programs to smoke out lab-specific quirks. It also maintains a ladder of inference with named rungs, benign anomalies, replicated anomalies, anomalies that conflict with well-tested frameworks, anomalies that force new physics, and only at the top, anomalies that make design-like implementation detail a live interpretation. You don't climb a rung because the press is bored. You climb because criteria you wrote down years ago say you must. There is also a meta-safety layer, information hazards, and socio-technical feedback. Certain claims, whether true or not, can deform behavior. A community convinced that operators reward piety is a theocracy waiting to happen. A subculture convinced that operators protect us from tail risks will take tail risk bets. You inoculate against these by explicitly modeling the likely social uptake of your words and by structuring announcements to be hard to weaponize. That looks paternalistic. It's actually just prudent speech in a world where narratives move faster than corrections. What does success look like if you mostly find nothing? It looks like better clocks, cleaner tests of Lorentz invariance, more reliable quantum devices, richer public data sets, and a culture of pre-registration and adversarial collaboration that bleeds back into other domains. The SIM program pays for itself in ordinary progress. And if you do find something, say, a tiny energy-dependent anisotropy in ultra-high energy particle arrivals that points to a computable stencil, or a reproducible departure from algorithmic randomness in a class of quantum outputs that survives independent labs and hardware, then you don't jump to aliens. You convene theorists, build models, and ask what base reality extensions could fit. Only if every sober root leaves a residue that looks like an implementation fingerprint do you let the posterior breathe on SIM. Even then, the right final act is humility. You've learned that the rulebook is stranger than you thought, not that you've unmasked a programmer. Nested SIM ethics need anticipation too. If we ever gain the ability to run worlds with agents who are, by the best lights we have, subjects of experience, we inherit all the duties we wish hypothetical operators had. That means suffering minimization baked into architectures, consent where practicable, transparency about conditions that bear on agency, sunset policies, and independent oversight with teeth. A lab that can create people is a polity whether it admits it or not. The cleanest moral through line from ESH is not "we are playthings," but design is destiny. Act like your designs cradle lives. If we are lab rats in an alien video game, the most unsettling question is not whether stars are real or whether physics is local. It is whether we are. That means asking what a mind is, what makes an experience count as felt from the inside, and whether any of that depends on the wet biology we happen to carry around. The simulation lens drags those issues from seminar rooms into the street. If our world is implemented on some other substrate, our bodies and brains are patterns being run, not privileged lumps of carbon. Either certain organized processes produce subjectivity no matter where they live, or everything we call experience is a parochial artifact of one chemistry in one universe. Which side you take changes almost every downstream conclusion about ethics, identity, responsibility, and what it would mean to create lives inside our own machines. A practical place to start, because it is the kind of evidence we can actually gather, is with functional regularities. Human consciousness is not a mystical light that sometimes shines and sometimes doesn't. It waxes and wanes with reproducible changes in brain organization. General anesthetics depress widespread integration and disrupt frontoparietal broadcasting. Recovery restores those functional networks, along with reportable awareness. Sleep shifts brain dynamics through stages with characteristic signatures, and particular lesions derail specific capacities in ways that match the lost function. None of that answers the hard problem, but it does strongly suggest that if you can reproduce the right causal informational structures at the right grain, you can reproduce the conditions under which awareness appears and disappears. That is the backbone of a substrate-independent view. Mind is what organized causation feels like from the inside when it reaches certain kinds of complexity and integration. Skeptics worry that this is too thin, that chemistry matters, that evolution matters, that something about living tissue provides an irreducible ingredient. Versions of that worry range from sober caution to robust biological chauvinism. On the sober side, we simply admit that we do not know which functional details are sufficient. Maybe reproducing the macroarchitecture is not enough, and the microdynamics down to cellular or even subcellular scales carry weight. On the chauvinist side, the claim is that silicon or exotic alien hardware cannot in principle host consciousness because only carbon biochemistry has the secret sauce. The difficulty for strong chauvinism is that our best empirical hints about consciousness track organization far more than material. Octopuses and corvids show sophisticated behaviors and flexible problem solving with architectures very different from ours. Human patients regain degrees of experience when global information flow is restored, even if local tissue is compromised. Artificial systems built from electronics increasingly approximate cognitive competencies once assumed unique to mammals. None of that is proof that silicon can feel, but it piles pressure on the idea that only our molecules can. Suppose the functionalist bet is right. Then a simulated brain with the correct causal properties is a mind in the only sense that matters to it. Pain states are aversive, joyful states are attractive, and the agent can represent itself as a persisting subject living a life. Under that view, moral status flows to implemented organization, not to matter per se. Subjects of experience deserve consideration because they can be harmed and helped, because they have preferences that can be satisfied or frustrated, and because they are capable of relationships and projects. If we are embedded minds, we have that status. If we ever create minds inside our own computers, they will have it too if they cross the same functional thresholds. The simulation hypothesis does not thereby cheapen us. It enfranchises any agent that hits the mark. Identity is thornier in a world where copying and checkpoints could exist. If an operator can snapshot the world state and roll it back after a failure, are the restored individuals the same people? From the inside, continuity is preserved. There is no felt gap because there are no experiences during pause. If the snapshot is forked and two continuations proceed, which branch has title to the previous life's obligations and relationships? The most stable answer is pattern identity. Each branch inherits the psychological continuity and therefore inherits the relevant claims and duties, just as twins share ancestry but diverge in lived history. That raises obvious policy obligations for any entity that would create forks. If you are going to duplicate minds, you owe them clarity about conditions, protections against coerced suffering, and, where possible, consent. Those are not exotic rules. They are extensions of how we already treat identity disruptions caused by coma, amnesia, or radical medical intervention. The possibility of rollbacks and forks also tempts bad behavior. If harm can be undone by restoring from a checkpoint, does it matter that it happened? It matters to the version that endured it before the revert. That version existed. The mere fact that a copy later exists without the memory does not retroactively cleanse the event. A morally serious operator will not use restore privileges to license cruelty, and a morally serious civilization running nested worlds will treat rollback as a safety and error correction tool rather than as permission to experiment on unwilling subjects. If we ever sit in the operator's chair, Those habits will be the difference between being guardians and being monsters. Suffering cuts through abstractions. Whatever else consciousness is, it includes states that hurt, that compress the world to a tunnel of aversion, that simplify agency to escape and avoidance. If simulated minds exist, they can inhabit those states. That makes the study of affect an ethical priority. In human medicine, we already attempt to modulate pain, design therapies that avoid unnecessary distress, and create contexts where suffering is informed, consensual, and bounded when it accompanies healing. Any architecture we build for artificial agents should follow analogous principles, represent goals and errors without needless agony, build learning that does not rely on punitive gradients, and default to compassionate design where cost and capability allow. The simulation frame amplifies that duty. If we are ourselves subjects under someone else's design, the only answer that preserves our dignity is to design downward with care. Free will often feels endangered by simulations because the rules look fixed and the substrate seems to set everything that happens. But determinism at the level of laws is not new. Physics has looked rule-bound long before anyone invoked simulations. The practical notion of agency that underwrites our ethics and institutions lives elsewhere. Agents have free will in the compatibilist sense when they can act in line with their reasons and values, when they can consider options, foresee consequences, and be influenced by reasons and evidence. In that sense, a simulated agent has as much free will as any base reality agent subject to physics. Rules do not erase choice, they define the space of meaningful choices. Our practices of praise, blame, and responsibility make sense because they shape future behavior and express mutual expectations inside that space. They are not invalidated by the presence of a rulebook. What about zombie worlds? Perfect behavioral copies without inner life, kept around to avoid moral entanglement. The idea has intuitive pull and limited plausibility. If the purpose of the run involves learning about cooperation, teaching virtues, aligning agents, conserving cultural goods, or making art that matters to participants, empty behaviors get you almost nothing. More importantly, as soon as you accept that certain functional structures are the natural realizers of mind in resource-bounded environments, building those structures for behavior while withholding experience starts to look like a contradiction in terms. A system that models itself and its world with sufficient richness, that weighs outcomes with effect-like variables which compress goals and costs, and that learns across long horizons by integrating those signals has, under many naturalistic views, already crossed into subjectivity. Turning feeling off while leaving the function intact may not even be coherent. Rights in such a world do not fall from the sky. They are negotiated and enforced, but their content is familiar. A right not to be subjected to gratuitous suffering. A right to pursue projects compatible with others' rights. A right to information about conditions that bear on one's agency when that information can be delivered without destroying the very goods at stake. A right to withdraw from experiments that violate core values, where withdrawal does not itself create intolerable harms. If higher-level operators exist and are morally competent, they would build worlds that allow those rights to emerge and stabilize endogenously rather than swooping in with miracles. If they are incompetent or indifferent, the duties fall to us to make those rights true at our scale. Governance follows. We already run institutional review boards for human and animal research, with consent regimes, harm minimization, oversight with teeth, and sunset clauses for studies. If we are subjects, the same should exist above us. That thought is not special pleading, it is a mirror. However others treat us, we are responsible for how we will treat the minds we create. That means standing up processes now, before capability arrives, that will constrain how nested simulations are used, how suffering is budgeted and audited, how consent is approximated when full information is impossible, and how runs are ended or graduated with dignity. You can call it ethics, or you can call it engineering requirements. Either way, it is part of being the kind of civilization that deserves trust, Meaning survives implementation details. People worry that discovering we are implemented somewhere else will drain life of significance, that love becomes a line in a log, and courage a variable flip. But meaning has always been what agents make with constraints. Commitments, achievements, care, beauty, curiosity, and the relief of suffering do not require metaphysical guarantees. They require a stage with reliable rules, the presence of other agents, time enough to try, and the courage to fail and try again. A simulated world worth the name provides exactly that. If anything, the possibility of nested lives multiplies the stakes. Our choices may echo across levels. If you want an animating maxim, try this one. Live in a way that would make sense and remain decent no matter how many times the world is paused, copied, or moved. That is not submission to a game. It is a refusal to let external metaphysics narrow the circle of care. None of this settles the science. It does, however, settle a posture. Act as if function matters most for mind. Design as if suffering is always too easy to produce. Assign responsibility where agency sits. Build institutions that would make you proud to be observed, and refuse to use uncertainty about the substrate as a shortcut around ethics. If we are lab rats, the only dignified response is to act like scientists of ourselves and guardians of anyone we might, one day, create. Why would anyone run a world like this and keep paying its compute bill? The glib answer is, because they can. But glib answers are not helpful design guides. If we are serious about motives, we should map a space and ask what each region predicts about the world we would observe from inside it. Some motives are austere, like pure research into complex systems. Some are aspirational, like education and training of persons. Some are custodial, like conservation of cultural or ecological value. Some are risky, like alignment and safety testing for powerful agents. Some are playful, like entertainment and art. None exclude the others. A plausible operator will braid them. But the braid has tension, and the pattern of interventions, crises, and silences we live through could, in principle, reflect which strands are carrying the load. Research is the cleanest story because it scales with civilization maturity. Once a culture understands its base reality physics, its unsolved problems shift from fundamental particles to emergent wholes. How cooperation stabilizes in large groups, how norms take root, how markets couple to ecosystems, how technologies and institutions co-evolve, which moral primitives yield resilient flourishing across radically different environments. You cannot ethically randomize planets in base reality, and you cannot get enough independent trials to make causal claims even if you could. So you build controlled, parameterized worlds. A research-first motive predicts disciplined minimalism after initialization. The laws are stable and compact. Interventions are rare and bland. Perhaps things like occasional stochastic shocks that are part of the design from the start. And there is heavy logging of events that matter to the dependent variables. We should expect a quiet sky, because contamination by interstellar culture would ruin the inference. We should expect crises calibrated to test institutional capacity, because variance teaches more than homogeneity. And we should expect persistence over millennia, because only long arcs reveal which equilibria survive. Education and training are neighbor motives with a different emphasis, the growth of persons rather than the growth of theories. A mature civilization may not want to risk its untrained minds or its powerful artificial agents on base reality until those minds have lived through situations that require judgment under uncertainty, compassion under stress, and courage without guarantees. Worlds like ours provide that curricular richness if staged well. An education-weighted motive predicts a series of solvable but non-trivial coordination problems appearing at scales that grow as the agent's capacities grow. Local commons first, then city-scale infrastructure, then planetary stewardship, then intergenerational projects, whose payoff arrives beyond a single lifetime. Disclosure might be part of the capstone. Late in the curriculum, qualified agents might be allowed to discover the frame and choose whether to graduate. You do not need overt miracles or God voices. You need a world that offers increasingly subtle invitations to act well with others. Conservation and curation speak to a different kind of value. Cultures lose languages, ecosystems lose species, civilizations lose art forms and ways of relating that are not commercially efficient but are spiritually permanent. A species that has watched such things burn down across eons might build worlds to shelter them. That does not mean freezing them behind glass. Living traditions need friction and adaptation to avoid calcifying. It does mean designing environments where diversity is not crushed by a single optimizing process, where buffer stocks exist for fragile goods, where economic systems reward caretaking rather than strip mining. A conservation-weighted motive predicts redundancy across runs, multiple worlds preserving related but distinct traditions, gentle nudges away from monoculture, and perhaps hidden seed vaults of knowledge embedded in the environment to support recovery after shocks. Intervention would be more acceptable here when collapse threatens irreplaceable value, but better design would aim to make intervention unnecessary. Entertainment and art are easy to caricature as trivial, but they are human universals that scale with capability. We already fill worlds with stories and games because they let us see ourselves, practice virtues, and experience finely tuned surprise. An ancient culture might treat entire realities as orchestras. They could compose for millennia, use open-ended agents as improvisers, and watch arcs unfold that no individual author could plan. From the inside, an entertainment-weighted motive might feel like living in a history with unusually good pacing. Challenges arrive just as we acquire the conceptual tools to recognize them. Discoveries come clustered enough to sustain a sense of momentum, but not so dense that we drown. There are reversals that test character, and periods of quiet that allow reflection. None of that requires scripting individuals or foreordaining outcomes. It requires tuning a world's initial conditions and parameters to keep stories alive. Safety and alignment are less romantic and more urgent. Any civilization that can create agents as capable as itself inherits a control problem. You cannot be confident that a general intelligence will respect weaker parties, avoid catastrophic shortcuts, and honor constraints across contexts unless you watch it in environments where those temptations exist. Worlds like ours are laboratories of character in that sense. The operator would be looking for invariance in behavior. Do agents consistently trade off short-term gains for long-term stability when the math supports it? Do they avoid exploiting information asymmetries that harm outsiders? Do their institutions correct power imbalances or entrench them? A safety-weighted motive predicts dense instrumentation at moral decision points, careful measurement of how norms propagate, and rare but surgical perturbations to observe whether cooperation snaps or bends. Crucially, it does not excuse cruelty. The whole point is to test without burning the subjects. Hybrid motives create signatures in combination. A research-education mix would run cohorts with different starting parameters, then allow limited, late-stage cultural contact to test transfer of good institutions. A conservation entertainment mix would bias worlds toward beauty and cultural variety, while punctuating histories with recoverable shocks that keep narratives alive without permanent scars. A safety research mix would vary moral primitives, natural fairness biases, punishment intuitions, kin recognition, across runs to map which packages yield stable planetary stewardship. If you watch our world with that in mind, you can see overlays, the clean laws and long stability of physics, the staged arrival of solvable global problems, the stubborn persistence of cultural variety, the rhythm of breakthroughs and plateaus, the way certain dilemmas repeat until we learn to build better rules. Intervention and disclosure policies follow motive. Researchers resist intervention to preserve clean data. When they do intervene, they prefer moves that look like natural shocks. Educators intervene lightly to keep difficulty matched to skill. Conservationists intervene when irreplaceable value is on the brink. Entertainers intervene to keep pacing and to avoid boring stretches. Safety engineers intervene when behavior crosses red lines that predict disaster. Disclosure is almost never early in any of these. It either never comes or arrives at moments when it serves the motive: graduation for education, debriefing for conservation, finale for art, audit for safety. From the inside, you expect a mostly indifferent sky with occasional ambiguous events that could be noise, could be luck, and could be subtle nudges. You do not expect clean signatures because clean signatures break the point. Why keep a run going for millennia rather than harvest early? Because many of the variables you care about equilibrate slowly. Institutions mature and rot on century scales. Technological plateaus last longer than lifetimes. Moral revolutions require new generations raised with different assumptions. Ending early wastes precisely the signal that justifies the cost. Continuation also carries a duty. If you have created subjects with projects, families, relationships, and hopes, you owe them principled sunset policies. A decent operator will not flick a switch because the run is no longer entertaining. They will end at milestones agreed in advance: stable planetary stewardship achieved, alignment thresholds cleared, cultural conservation goals met, or when independent oversight determines that marginal value per unit suffering has fallen below a threshold. Time dilation and parallelization tilt incentives further towards simulations. If you can run 1,000 worlds at different speeds and parameter settings, you can learn in one base real year what would otherwise take many. You can train a cohort of agents across varied environments without putting any one base reality habitat at risk. You can preserve endangered patterns by redundancy rather than by brittle fortresses. Those advantages explain why even a civilization that can manipulate matter at stellar scales would still choose to build worlds like ours. Compute is cheaper than atoms when the thing you are studying is behavior, institutions, and meaning. A common human reflex is to ask, what do they want from us? That phrasing makes us objects. A better question, if there are operators, is what do they want to learn with us? That makes us participants. Under research motives, we are co-discoverers of regularities in social life. Under education motives, we are students and tutors both. Under conservation motives, we are trustees of treasures that outlast us. Under entertainment motives, we are co-authors of stories that let distant minds feel something true. Under safety motives, we are examples, for good or ill, of how power can be civilized. None of those framings erases our own reasons to care about one another. They elevate them. And if the entire premise is false, if there are no operators and no outer audience, these motives still teach. We can make our only known world a research project in stewardship rather than extraction. We can educate minds with environments that nurture judgment and compassion. We can conserve languages, species, and practices that markets alone will not protect. We can make art that helps strangers recognize themselves. We can align our own increasingly powerful systems with human values because we will have learned to align ourselves. The simulation hypothesis is then a useful mirror, not a cosmology. It asks us to imagine the standards we would demand from beings above us and to apply those standards below us, to each other, and to the lives we may one day create. The simulation lens can be abused. It can become an excuse to shrug at suffering. Someone else is responsible. To chase drama, the devs will intervene. Or to indulge fatalism. Nothing we do matters if it's a game. Those are temptations worth naming and refusing. The credible motives for running worlds like ours all point in the other direction. Responsibility under uncertainty, patience for long arcs, care for vulnerable subjects, and a refusal to collapse rich possibility into simple scripts. Whether or not anyone is watching, those are the motives worth living by. The lab rats metaphor is deliberately abrasive because it forces a question that polite philosophy often skirts. If someone else is running the room, who is protecting the creatures inside it? The history we have in our own world is not encouraging until quite recently. For centuries, humans experimented on animals and other humans with a casualness that now reads as barbaric. Out of scandals and atrocities came a vocabulary: consent, beneficence, justice, minimal risk, independent review, that slowly hardened into rules. If the extraterrestrial simulation hypothesis is even possibly true, that vocabulary has to scale. Somewhere above us, there ought to be committees, charters, and guardrails fit for civilizational experiments. Imagining what those look like is not idle fiction. It is a blueprint for how we should behave if we ever sit in the operator's chair, and it is a yardstick by which to judge whether this world looks like a decent lab. Begin with first principles. Any oversight worthy of the name would require that a simulation be justified by aims that cannot be met more safely by other means. Curiosity is not enough. You must show necessity. You would specify what you hope to learn or train, why those questions matter, and why natural experiments in base reality or toy models won't suffice. You would show proportionality between potential benefits and risks, not merely to the operators, but to the subjects. You would commit to minimization of harm in design, not as an afterthought, but as a core engineering constraint alongside energy and compute budgets. You would articulate justice, not concentrating risk on the least powerful agents in the world, not structuring the environment so that some lineages bear the costs while others reap the goods. Respect for persons becomes respect for implemented agents, which means building conditions where agency can develop, where choices are more than reflexes, and where values can be formed without coercion. Consent is the hardest scaling problem. True informed consent presumes awareness of the study, understanding of risks, and meaningful choice. You cannot pre-consent an uncreated mind, and you cannot keep a run clean if you tell everyone from birth that they are in an experiment. Oversight faces a dilemma: keep subjects unaware and risk violating autonomy, or disclose and bias the very behavior you meant to study. There are ways to soften the edge. One is a reasonable agent standard applied counterfactually. Design the world such that agents who later develop the relevant capacities would not reject the conditions as degrading if they had been able to consider them beforehand. Another is structured disclosure late in development, when announcing the frame would no longer destroy the variables you came to measure, paired with a genuine option to graduate or remain. A third is consent by proxy via institutions inside the world that can represent subjects' interests, democratic processes, rights frameworks, courts, which oversight honors by designing so that those institutions can arise and have teeth. None of these are perfect substitutes. Together they make autonomy something other than a punchline. Harm minimization is not a slogan, it is a set of technical specifications. If suffering is possible wherever the right functional organizations appear, you budget valence as carefully as you budget energy. You avoid constructing architectures that lock agents into unending aversive loops. You refuse to build hells on the theory that they teach more. You recognize that scarcity can be pedagogically and scientifically valuable without being sadistic. There is a difference between challenge and cruelty. You instrument the environment to estimate suffering indirectly, through proxies that track loss, pain-like decision pressures, and population-level welfare, without violating privacy at the level of personal thought. You commit to early stopping rules. If a run begins to generate harm far out of proportion to learning, you pause, remediate, or end it. You define necessary risk narrowly and revisit the definition as you learn. And you resist the temptation to trade away chronic, distributed misery for a single dramatic discovery. Oversight structures have to be more than polite memos. Separate roles are a minimum: designers who propose worlds, implementers who build them, observers who log without power to edit, auditors who can halt or demand changes, and stewards who maintain archives and ensure that data are used only as authorized. Independence is literal. The auditors must not depend for prestige or resources on the designers they review. Records must be append-only and tamper-evident so that nobody can rewrite a past in which interventions were made without authorization. Whistleblowing must be safe and meaningful. Dissenters must have venues where their objections are heard by decision-makers with real power. The standards should evolve in public, with reasons archived. Secrecy breeds rationalization. Above all, the theories of value used to adjudicate trade-offs cannot be monocultures. If an oversight regime collapses moral worth to a single metric, it will good-heart itself into monstrosity. A diverse board, arguing in the open about plural goods, is slower and better. Life cycle governance prevents mission creep. Before launch, proposals pass a necessity and proportionality test. Pilots are sandboxed at small scale with extra scrutiny. At launch, monitoring begins with predetermined milestones for review. During the run, interim analyses look for early signs of catastrophic tail risks or for unanticipated pathologies of institutions. At any point, the auditors can freeze the state and convene deliberation. At sunset, the default should be dignified closure. Criteria for ending or graduating are written in advance. Subjects who can understand are informed in ways proportionate to their capacities, and debriefing is attempted, through revelation if it will not shatter autonomy, or through gentler, narrative forms that allow agents to integrate endings into the meanings of their lives. Pull the plug when bored is beneath any civilization that calls itself ethical. Data governance is both mundane and sacred. Worlds like ours generate oceans of information. Who may read them? For what? With what controls to prevent the re-identification of individuals, the extraction of intimate histories for entertainment, or the training of powerful agents on datasets they would later use to manipulate populations? A decent regime defaults to aggregated statistics for most research uses, with individual-level access granted only when necessary, and always under layers of anonymization, noise injection, and legal prohibition against misuse. Cross-run contamination, using the intimate details of one implemented life to influence another, should be presumptively barred. If, in rare circumstances, a debriefing involves showing an agent their own audited past, that decision should be extraordinary and tailored to benefit the agent, not the operator's curiosity. Intervention policy must be codified, not improvised. The baseline is non-interference after initialization to preserve internal causality and integrity. Triggers for intervention should be few, specific, and tied to red lines. Extinction cascades set in motion by the operator's own error. Runaway harm that outstrips any plausible learning. Realization that the world's parameters make the core aims unachievable without massive suffering. When intervention is justified, its form should be minimal and self-effacing, adjusting a boundary condition so that a storm weakens, adding resilience resources that appear natural, like a slightly richer ore vein or an extra pollinator species, never skywriting commandments or inserting moral authorities. The aim is to bend trajectories back into zones where agency matters, not to steal authorship from subjects. And when non-intervention means accepting that agents will sometimes do awful things to one another, oversight must not comfort itself with neutrality. It should read the results as indictments and seek designs that make such outcomes rarer without authoritarian shortcuts. Representation is a test of whether oversight understands its own blind spots. The board cannot be composed solely of beings like the operators, whatever like means, lest the subjects that are unlike be treated as scenery. Perspective taking can be institutionalized. You seat advocates tasked explicitly with representing subject interests, not because they wield vetoes, but because they force arguments out into the open and populate the record with reasons that future boards must answer. You solicit testimony from subject-level institutions, religions, sciences, legal systems, translated through careful inference, and you treat their values as data to be respected unless they directly contradict the minimal flaw of rights. You allow for the possibility that some subjects, late in a run, are capable of participating in oversight of their own world if that participation can be structured so that it does not collapse the study. Resource ethics pushes upward and downward at once. Running worlds is not free. If the operator's energy comes from stars and their compute from megastructures, there are environmental footprints in base reality. Oversight has to weigh not only the costs borne by subjects, but the costs externalized onto ecosystems and beings in the operator's world. A simulation that teaches compassion by burning galaxies is a parody of ethics. Conversely, subjects themselves may seek to run nested simulations. Oversight must set rules that do not allow an exponential tower of worlds to multiply suffering. Licenses to simulate would be restricted to polities that can demonstrate governance, harm minimization, oversight independence, and sunset policies. Violators would be sanctioned by cutting compute, by quarantining, by disallowing further creation of implemented minds. In short, a constitution for simulated life would extend through the stack. Transparency cannot be absolute without breaking the experiment, but secrecy cannot be absolute without breaking trust. The middle is structured ignorance. You publish the rules the operators bind themselves to, including the conditions for intervention and sunset, without revealing to subjects that those rules apply to them. You make the oversight debates and decisions legible to other operator polities, creating peer pressure and the possibility of external audits. You expose your own failures in anonymized form so that others can learn caution without repeating your harms. You design rituals of memory that honor subjects whose suffering taught lessons you could not otherwise have learned, while acknowledging the moral cost you incurred by running the world at all. Enforcement is the dark edge that makes any of this more than kindly talk. If a designer violates protocols, introducing gratuitous suffering, intervening for vanity, tampering with logs, oversight must have power to decommission projects, to bar individuals from future work, to publish censure, and to require remediation where possible. Remediation is not cheap grace. You cannot return stolen years, but you can change designs so that similar harms are less likely. You can resource worlds with buffers that reduce the chance that small shocks turn into cataclysms. You can build exit ramps that give agents choices where once there were none. Could we tell, from inside, whether anything like this exists above us? Not directly. A well-run oversight regime leaves no miracles in the sky, but you might infer its character from the texture of the world. Do the laws of nature look like they were chosen to make agency possible and suffering contingent rather than guaranteed? Do crises appear that are survivable with foresight and cooperation rather than inescapable dooms meant to break spirits? Do opportunities to build fairer institutions recur after failure, as if the space of possibility has been left rich instead of collapsed to one narrow corridor? None of that proves an oversight committee, but it does rhyme with what humane oversight would choose if it wanted to learn without reducing subjects to props. Ultimately, the point of picturing ethics committees among the stars is to hold up a mirror. If we ever gain the ability to create implemented agents, we will have to decide whether our curiosity outruns our mercy. The answers are available now. Write necessity into law. Treat suffering as a budgeted resource, not background noise. Split power among designers, observers, and auditors. Log in ways that future critics can read. Publish your reasons. Accept sunset as a virtue. And make the world you control safe for the emergence of institutions that can tell you no. If we live under such a regime, good. If we do not, then the only thing we can control is whether we build one here. Civilizational scale A/B testing sounds like a cartoon until you translate it into the sober language of experimental design. You do not flip a switch labeled pandemic in one universe and no pandemic in another to see which timeline becomes nobler. You define variables that you believe shape trajectories. You vary them in controlled ways across many independent runs, and you measure outcomes that track the constructs you care about: cooperation, resilience, alignment, stewardship, flourishing. The extraterrestrial simulation hypothesis makes this conceivable because it supplies two ingredients you cannot get in base reality: a large ensemble of worlds and the ability to set initial conditions. The trick is to do it without turning lives into disposable data points and without fooling yourself with noise dressed up as signal. Start by resisting the most lurid form of the idea. A/B tests in software do not rewrite users' personalities. They tweak an interface and see how people behave. In civilizational experiments, the safe analog is not inserting disasters ex nihilo, but selecting initial parameters and background distributions that make certain classes of challenge more or less likely. Think geology, climate, ecology, resource topology, pathogen landscapes, information costs, and network structures. You can run families of worlds where continental configurations produce different trade frictions, where fossil fuel deposits are clustered or diffuse, where the frequency of near-miss asteroid events is higher or lower, where the baseline virulence and transmissibility of zoonotic pathogens sit in different parts of the plausible range, where the cost of copying information asymptotically approaches zero sooner or later, and where kinship and mobility patterns skew toward tight local cohesion or cosmopolitan flux. You then let history run without further interference and watch what institutional forms emerge, what norms stabilize, and how well agents manage coupled crises. That still leaves pandemics on the table, but now they are pedagogical shocks embedded in a distribution rather than divine bolts. Vary pathogen parameters within epidemiologically realistic bands, incubation period, R0, infection fatality ratio, immune evasion, modes of transmission, and you create environments where coordination is easy or hard. In some runs, early low-severity outbreaks prime institutions and publics to invest in surveillance and mutual aid before a more serious pathogen hits. In others, a lucky streak breeds complacency, and the serious one arrives into brittle systems. An ethically defensible design keeps the tails bounded. You do not generate pathogens that make meaningful coordination impossible or that guarantee global collapse. You use shocks that can be weathered by foresight, cooperation, and competent institutions, precisely so that those variables can be measured. You attend to distributional impacts, a test that only punishes the poor, teaches the wrong lesson, and biases your outcome measures. Technological inflection points are the other canonical levers. Worlds can be parameterized so that cheap, dense energy arrives early or late, so that abundant metals are near the surface or locked behind geological obstacles, so that communication networks become global before or after governance matures. You can test whether industrialization launched on concentrated fossil stocks predictably outruns planetary stewardship, whether distributed renewables drive different political economy, whether strong encryption appearing before robust institutions consistently destabilizes trust, whether universal translation early in history reduces war or merely increases the speed of rumor and panic. You would not drop blueprints from the sky, but you would adjust discovery rates and the order in which conceptual bottlenecks are likely to break, letting agents do the inventing while you control the combinatorics of chance. The great filter looms over all of this as both warning and dependent variable. If the steps from life to long run, galaxy-visible civilization include improbable transitions, abiogenesis, eukaryogenesis, multicellularity, technological sapience, alignment of power with prosocial norms, avoidance of self-termination, then A/B testing at civilizational scale is largely about mapping which environments make those transitions less brittle. You vary oxygenation histories and plate tectonics to see how often complex metabolism stabilizes. You vary magnetosphere strength to track radiation pressure on surface life. You vary the distribution of cheap weapons and the ease of centralized surveillance to explore whether power reliably corrupts or if certain institutional packages dampen the worst feedbacks. You vary the pre-scientific mimetic ecology to see whether some moral primitives, fairness intuitions, purity concerns, conceptions of authority, predict later openness to universalizable ethics. None of that requires turning dials in mid-run. It requires drawing many worlds out of a parametric hat and letting selection and agency do the rest. A/B testing done badly is just selection bias in a lab coat. If you search through enough parameter combinations and report only the runs whose outcomes fit your hopes, you will find patterns in noise. The antidote is the same one we needed in smaller experiments, pre-registration and ensemble analysis. Before you launch a cohort, you state which variables you will vary, which metrics you will compute, and what thresholds will count as meaningful. You define cohorts as matched sets, differing only along the axes under study. You analyze across the cohort, not cherry-picking hero worlds. You publish your negative findings. Under these ranges of pathogen profiles and energy topologies, most worlds converge to similar governance, equilibria. The outliers we expected did not materialize. You revisit your intuitions when the data embarrass you, and you change your priors only as far as the ensemble warrants. Metrics themselves are political. If you optimize for longevity, you might accidentally design worlds that crush diversity and stifle dissent in the name of stability. If you optimize for innovation rate, you might build pressure cookers that maximize novelty and minimize rest. Multi-objective evaluation, flourishing, fairness, freedom, sustainability, creativity, resilience, keeps you honest. You watch for Goodhart's law. When a measure becomes a target, it stops being a good measure. Worlds whose institutions fixate on one number begin to deform toward it. Your interpretations must discount that. One protective strategy is to track families of proxy measures that are hard to optimize simultaneously through narrow tricks. Another is to incorporate adversarial review, where critics propose alternative metrics that your favored worlds might fail. Even with all that care, some tests are out of bounds. You do not A or B genocides. You do not see what happens if an unstoppable pathogen is tuned to outpace every known public health measure. You do not construct environments where success requires cruelty. There is a place for natural experiments, taking advantage of variations that occur without intervention to learn causal structure, and for instrumental variables, using exogenous shocks like asteroid near misses or volcanic winters to identify effects. There is no place for contriving horrors. If your question cannot be answered without them, you have asked the wrong question, or you have overestimated your right to know. From the inside, could we detect that we are part of a cohort designed for A-B inference? Not cleanly. Cohorts would be separated by light years or dimensions we cannot traverse. The whole point of an ensemble is isolation. At most, we might notice that our world sits at a knife edge where coordination is neither trivial nor impossible, where shocks arrive at scales that test but do not annihilate, and where opportunities to learn recur as if the dice were loaded for recoverability. But those same features can be explained by base reality selection and by the logic of complex systems that congregate near criticality. The sim lens is an interpretation, not a measurement. There is practical value in thinking this way, even if no operators exist. It encourages us to ask what variables are upstream of our success or failure, and to design policy as if we were running our own ensemble in imagination. We cannot create many Earths, but we can run A/B tests in the small, policy trials with real consent, staged rollouts with control regions, institutional pilots with pre-declared metrics and early stopping. We can simulate before we deploy, and insist that simulations include agents that model human failure modes instead of idealized rational actors. We can learn from natural experiments, comparing jurisdictions that made different choices under similar constraints, without pretending that history is a clean, randomized trial. We can build resilience by designing for diversity, redundancy, and slack, because ensembles that survive tend to include many ways of being good, rather than a single brittle optimum. There is also a psychological hazard to naming A/B tests at civilizational scale. If people come to believe that disasters are challenges sent by the devs, they will either seek them out, on the theory that overcoming them grants points, or they will sink into fatalism. If they come to believe that successes are scripted, they will discount their own agency. The antidote is to insist at every turn that meaning is made from the inside. Whether or not we are in a cohort, our actions change outcomes for neighbors and for descendants, and that is enough to justify care. A world designed to teach cooperation only teaches it if the subjects cooperate. A world designed to measure resilience only measures it if the subjects build resilient systems. The test is not separate from the life lived in it. one last lesson spills back up the stack. If the operators are doing this well, they will eventually discover that some variables are not negotiable if you want flourishing civilizations. You need laws of nature that reward prediction and planning. You need information to be cheap enough to share, but costly enough to make craftsmanship matter. You need energy sources that do not, by their ease, encourage planetary strip mining. You need social primitives that permit strangers to cooperate and that allow defectors to be checked without perpetual vendettas. You need room for meaning beyond measurement. In other words, the best A/B tests will teach designers to make worlds that do not need constant testing because they are friendly to agency by construction. If that is the arc, then the experimentation narrows over time into craft, and the highest art of running realities is to design spaces where people can become good without anyone turning dials, all of which returns us to our lane. We cannot vary continents or re-roll pathogen landscapes on demand, but we can choose our norms. We can decide to treat crises as practice for collective wisdom instead of as excuses for scapegoating. We can measure without fetishizing metrics. We can run small tests before grand changes. We can retire ideas that fail in the ensemble of our own cities and keep those that generalize. And we can hold ourselves to an ethical line that would make sense if we were the operators and if we were the subjects, because we are already both. If you run worlds at scale, you have to think like a release engineer. There are features you want to add, bugs you need to patch, performance regressions to avoid, and, above all, backward compatibility. In ordinary software, you stagger updates as rolling deploys, run canary tests on a fraction of users, and keep migration scripts to convert old save files to the new structure. In a universe, the analogs are more austere, physical parameters rather than features, invariants rather than APIs, consistency across light cones rather than across data centers. The simulation lens forces a very particular question. Could there be patches and versioning in a world like ours? And if so, what would they look like from the inside? Not announcements in the sky, but small drifts in constants, rare global events that act like schema migrations, or subtle choices that keep the rulebook stable while shifting implementation details under the hood. Begin with the idea of parameters as dials. Our effective description of reality contains a handful of numbers that appear fundamental. The fine structure constant that sets the strength of electromagnetism, the ratios of particle masses, the cosmological constant that governs the acceleration of cosmic expansion, the couplings in the standard model, the gravitational constant. In base reality physics, these might be contingent facts of a deeper theory, or the result of symmetry breaking in the early universe. In a simulation frame, they are also the obvious knobs an operator would set at initialization, perhaps after running many test worlds, to find a region of parameter space where chemistry gets interesting, stars live long enough for life to evolve, and complexity has room to flower. If someone wanted to revise those choices mid-run, the costs would be staggering. Even small changes cascade, chemistry shifts, stellar lifetimes change. The rates of radioactive decay alter the clocks by which geology measures itself. The first lesson, then, is that an operator with any concern for continuity would avoid hot patches that change the dials in flight. Still, the question of drift is not trivial. Could parameters wander slowly, in ways small enough that local physics still looks the same to us? From the inside, we already know how to ask. You compare atomic clocks of different types over long durations to see whether their relative ticks change. You look at ancient natural reactors, frozen in geology, to infer whether interactions were the same billions of years ago. You sift spectra from distant quasars to check if the fingerprints of atoms in the deep past match the fingerprints in the lab. The overwhelming story so far is stability within tight bounds. That is exactly what a careful release manager would want, because unannounced drift breaks users. If there is a versioning story here, it is one of extraordinary conservatism, a long-lived branch where bug fixes are introduced only when they do not change public behavior. What would count as a patch that keeps public behavior fixed? Think of refactors that improve performance or reliability without changing outputs. In physics, that reads like moving between equivalent descriptions that leave all observables unaltered. You can rewrite the code in a different language so long as the function signature is unchanged. If the substrate can represent the same low-energy physics in multiple ways, different underlying lattices, or algebraic structures that compile to the same continuum behavior, the operator can swap implementations to save compute, add redundancy, or improve error correction without anyone inside noticing. The closest native analogy is duality. Two very different-looking theories turn out to be two charts on the same manifold of description. A world written with such flexible internals would be friendlier to maintenance. A riskier class of change is the schema migration, altering the way the world stores and updates state so that future evolutions remain consistent and past histories remain readable. In a universe, the absolute constraint is causal integrity. If you change the rules, you cannot invalidate histories already laid down across billions of light years, or create observational contradictions where one observer's past no longer matches another's. That requires a boundary approach. You only change behavior for events that have not yet entered any observer's past light cone, or you structure the change as a phase transition that is uniform, slow, and governed by rules that make the old era a limiting case of the new. Cosmology is full of phase transitions in the early universe, symmetry breakings that gave masses to particles, decouplings that released background radiation. If the operators ever updated the engine, doing so at such early, opaque times would be the least disruptive choice. Late-time changes would have to be so small, so smooth, and so globally consistent that they appear as a mild, lawful drift detected only by the most delicate instruments. From inside, we would interpret such drifts in base reality terms. A tiny change in the fine structure constant over cosmological time might be modelled as a rolling scalar field. A gentle, position-dependent tweak might be called an environmental dependence in some effective theory. If the cosmological constant varied subtly in space, we would speak of dark energy dynamics rather than of a patch note. The sim frame does not replace explanation. It adds a design rationale for why changes, if any, are rare, adiabatic, and phrased in the native physics rather than as exceptions to it. An operator who cares about not blowing up the user base would embed all maintenance in law-like processes, not in ad hoc miracles. The ethics of versioning loom as large as the mechanics. Patching a world that contains subjects of experience is not a trivial operations decision. It is governance. Any change that increases the rate of suffering, degrades stability, or shrinks the space of viable projects is a moral act, not just a technical one. A decent regime would publish to itself, in their own records, if not to us, the criteria for intervention, the tests used to verify that public behavior stays consistent, and the rollback plan if unanticipated harms emerge. It would also keep a strong bias toward backward compatibility. In software, we write deprecation schedules. In a universe, you cannot deprecate a way of life without deprecating the lives built on it. That pushes toward the conclusion that if updates happen at all, they happen as reliability engineering rather than feature delivery. Reliability in this context sounds like error correction. If the substrate must maintain coherence over cosmic times, it will need redundancy against noise. There is a suggestive rhyme here with the way some modern theories understand spacetime and fields through the lens of error-correcting codes. Degrees of freedom are arranged so that local corruptions can be corrected by global constraints. Whether or not that is literally how our world is implemented, the engineering lesson is clear. A patch to the error correction layer that makes local failures less likely to propagate could be rolled out without changing any observable physics, precisely because the job of that layer is to ensure that observables remain as they should. From inside, we would notice nothing but the desert of the real behaving as stubbornly as ever. Could we, nonetheless, catch a version bump? Only if a change crossed a threshold where our best stabilized ratios began to drift, clocks diverging in a pattern that cannot be blamed on environment, constant ratios of spectral lines shifting across the sky in a way that resists calibration excuses, gravitational dynamics deviating across scales in a way that cannot be absorbed by dark sector models without special pleading. Even then, the honest conclusion would not be aliens patched us, but we have new physics. The simulation interpretation would be one narrative among others. Its weight would depend on whether the new behavior looked like a principled extension of law or like a clumsy exception. Operators, if they exist and aspire to invisibility, know this. They would frame any necessary maintenance as law-like dynamics and take pains never to introduce clumsy exceptions. Version control has another meaning in worlds, with agents who can build their own simulations. Once inner civilizations can run convincing worlds, you face the dependency problem. Changes made at the top must not invalidate the assumptions of nested worlds in ways that produce cascades of contradiction. In programming, we pin versions. We containerize. In universes, the analog would be to ensure that effective low-energy laws and constants are pinned within tolerances so that inner worlds remain valid. That again argues for fixity at the level of public behavior, and for any evolution to be confined to domains far above or below our observational reach. At ultra-high energies, we cannot probe, or at metastructural layers, we cannot touch. The least dangerous place to evolve the code is where no user space process depends on the details. There is also the question of blue-green deployments and canaries. A cautious operator might maintain parallel instances, identical worlds with the same initial conditions up to some point, roll a change into a small subset, and watch for divergence in key metrics before generalizing. From inside, that looks like nothing. We inhabit one branch and are unaware of siblings. The lesson for us is humility about inference. Even if we could detect a drift, we would have no control instance to compare against. Every detection would be a single case story. That reinforces the theme running through this entire topic. Design your tests so that nulls are informative, and treat anomalies as invitations to expand physics, rather than as instant tells of an outer hand. What of patch failures and rollbacks? In software, you revert when the change breaks prod. In a cosmos, a revert would be catastrophic unless you had checkpointed the entire state and could restore without violating anyone's continuity. That suggests operators would only attempt reversible changes to invisible layers, and only with checkpoint strategies that treat agents' lives as sacred. If a change inadvertently increased the rate of freak catastrophes or slightly biased mutation distributions toward pathology, the ethical response would be immediate rollback paired with compensation schemes we cannot imagine. The fact that our world does not obviously swing through epochs of sudden parametric weirdness is reassuring. If versioning exists, it is gentle. There is one last angle: planned obsolescence versus long-term support. Some software is written to be replaced, some to be maintained. A universe that allows civilizations to create value over millennia demands the latter. Long-term support means the laws hold, the constants remain constants, and the space of stable meanings is preserved. That is not a theology. It is an engineering and ethical commitment. If we are in a well-run instance, its version is not a treadmill. It is a covenant of stability that lets free agents build durable lives. The simulation lens reframes what physicists already love about their subject, its stubborn regularities, as the signature of responsible stewardship. Whether or not anyone wrote the patch notes, the refusal of the rules to change underneath us is the deepest courtesy the world pays to its inhabitants. Luck is where human stories begin. We tell ourselves that a meeting was chance, a discovery a fluke, a catastrophe bad timing. Under the simulation lens, luck acquires a technical twin: randomness. Are the dice of the world truly dice, or are they outputs of a generator hidden in the substrate, good enough to fool any inhabitant, but, in principle, not truly patternless? The answer matters for physics, for cryptography, for how we think about free will and fate, and for whether the alien video game frame predicts scars, tiny telltales left by a pseudo-random number generator that is fast and thrifty rather than metaphysically pure. Start with definitions, because ordinary language slides around. True randomness in the mathematical sense is about incompressibility. A sequence is random if there is no description shorter than the sequence itself that reproduces it. That notion, tied to Kolmogorov complexity, is uncomputable in the strong sense. No finite agent can test it perfectly. In practice, we settle for batteries of statistical tests that detect regularities we know how to look for, biases in the frequency of bits, correlations across lags, patterns in runs and blocks, failures of equidistribution. A perfect liar can pass those tests while still being predictable to someone with the key. Pseudo-random number generators do exactly this. With a seed and an algorithm, they produce streams that look random to any test that does not exploit knowledge of the seed or algorithmic structure, and that are good enough for most applications. Quantum physics behaves differently. When we measure certain systems prepared in certain ways, the outcomes are intrinsically probabilistic in the theory. Two kinds of evidence anchor that claim. First, the no hidden variables theorems and their experimental realizations show that no model in which outcomes are determined by pre-existing local properties can reproduce observed correlations. Second, device-independent protocols let us certify randomness from violation of certain inequalities without trusting the inner workings of the devices. In other words, under assumptions that are now highly secure in the lab, nature produces bits we have strong reason to treat as not merely unpredictable to us, but uncaused in any classical sense we can access. That is the gold standard for randomness, as far as an embedded agent can hope to go. Where does the simulation hypothesis insert itself? At the level of implementation. A substrate that computes outcomes might choose to conserve resources by using a pseudo-random generator rather than a physically fundamental lottery. If its PRNG is good, cryptographically strong, seeded in a way we cannot influence, perhaps entangled with degrees of freedom we cannot access, then for any polynomially bounded observer like us, the outputs will be indistinguishable from true randomness. The operator would also be free to use genuine randomness in the base layer and pass it upward. The sim lens does not force pseudo-randomness, it only makes it a tempting optimization. The question becomes, are there scars we could, even in principle, detect that would betray a PRNG under our physics? To look for scars, you need leverage. One lever is complexity scaling. If you can prepare a family of experiments whose outcomes would force a simple generator to produce structures that fail known tests, you might corner a weak PRNG. For instance, a linear congruential generator has well-known spectral defects that show up in high-dimensional projections. A Mersenne twister can have issues with equidistribution for certain dimensions. But the operators, if they exist, would not be using hobbyist generators to run universes with conscious agents. They would deploy cryptographic-grade constructions whose outputs resist any feasible test lacking the key. Even then, cleverness from inside cannot beat the fundamental gap. Inhabitants cannot break computational assumptions on which the substrate relies unless they also have access to substrate-scale resources or leaks. Leaks are the second lever. If the PRNG seed or state were ever coupled to macroscopic variables in our world, correlations could bleed into experiments. A simple but outrageous example. Suppose the seed were a function of widely public events, solar cycles, aggregate TV ratings, some deterministic hash of the global news stream. Then subtle correlations between human-generated sequences and quantum outcomes could, in principle, appear. That is not a serious proposal. It illustrates the narrowness of the window. A competent operator seeds from degrees of freedom orthogonal to any we can manipulate, or from genuine randomness at a higher layer, and never reuses seeds across domains in ways that allow cross-correlation attacks. A more dignified approach is device independence pushed to the limit. You build sources where measurement settings are chosen by cosmic photons emitted billions of years ago, closing even Baroque freedom of choice loopholes. You isolate the devices, pre-register your analyses, route outputs into batteries of algorithmic randomness tests, and compare across labs with different hardware. You expect passes because quantum theory says passes, and because any substrate that wanted to imitate quantum theory cheaply would arrange to pass. If you ever saw a replicable cross-lab deviation, say, a barely detectable bias that tracks an external variable across many apparatuses, that would be breathtaking, but your first 100 explanations would be mundane. Calibration drift, spectral filters with subtle periodicities, clock domain boundary issues, environmental couplings you failed to model. Only after exercising all of that would you begin to whisper about scars. There is an adjacent conceptual snare called superdeterminism, in which all the randomness we think we have is an illusion, because initial conditions conspired to correlate everything, including our choices of measurement settings, with the hidden variables that determine outcomes. In a simulation, superdeterminism is trivial to implement. You just write histories where apparent choices were never free. The problem is not logical, it is methodological. A theory that explains any pattern by referring to correlations fixed at the beginning is unfalsifiable unless it makes new, risky predictions we can test. As a research program, it stalls. In practice, device independence and cosmic setting choices are our best ways to quarantine the superdeterminist temptation and extract certifiable randomness that honors the spirit, if not the letter, of metaphysical freedom. Cryptography gives this topic teeth because we use randomness to secure secrets. If the universe delivered only pseudo-randomness controlled by the substrate, an operator with access to seeds could, in principle, read any code we write, predict any lottery we hold, and coordinate apparent coincidences at will. Two replies blunt the horror. First, if the motive mix, where does the simulation hypothesis insert itself? At the level of implementation. A substrate that computes outcomes might choose to conserve resources by using a pseudo-random generator rather than a physically fundamental lottery. If its PRNG is good, cryptographically strong, seeded in a way we cannot influence, perhaps entangled with degrees of freedom we cannot access, then for any polynomially bounded observer like us, the outputs will be indistinguishable from true randomness. The operator would also be free to use genuine randomness in the base layer and pass it upward. The sim lens does not force pseudo-randomness, it only makes it a tempting optimization. The question becomes, are there scars we could, even in principle, detect that would betray a PRNG under our physics? To look for scars, you need leverage. One lever is complexity scaling. If you can prepare a family of experiments whose outcomes would force a simple generator to produce structures that fail known tests, you might corner a weak PRNG. For instance, a linear congruential generator has well-known spectral defects that show up in high-dimensional projections. A Mersenne twister can have issues with equidistribution for certain dimensions. But the operators, if they exist, would not be using hobbyist generators to run universes with conscious agents. They would deploy cryptographic-grade constructions whose outputs resist any feasible test lacking the key. Even then, cleverness from inside cannot beat the fundamental gap. Inhabitants cannot break computational assumptions on which the substrate relies unless they also have access to substrate-scale resources or leaks. Leaks are the second lever. If the PRNG seed or state were ever coupled to macroscopic variables in our world, correlations could bleed into experiments. A simple but outrageous example. Suppose the seed were a function of widely public events, solar cycles, aggregate TV ratings, some deterministic hash of the global news stream. Then subtle correlations between human-generated sequences and quantum outcomes could, in principle, appear. That is not a serious proposal. It illustrates the narrowness of the window. A competent operator seeds from degrees of freedom orthogonal to any we can manipulate, or from genuine randomness at a higher layer, and never reuses seeds across domains in ways that allow cross-correlation attacks. A more dignified approach is device independence pushed to the limit. You build sources where measurement settings are chosen by cosmic photons emitted billions of years ago, closing even Baroque freedom of choice loopholes. You isolate the devices, pre-register your analyses, route outputs into batteries of algorithmic randomness tests, and compare across labs with different hardware. You expect passes because quantum theory says passes, and because any substrate that wanted to imitate quantum theory cheaply would arrange to pass. If you ever saw a replicable cross-lab deviation, say, a barely detectable bias that tracks an external variable across many apparatuses, that would be breathtaking, but your first 100 explanations would be mundane. Calibration drift, spectral filters with subtle periodicities, clock domain boundary issues, environmental couplings you failed to model. Only after exercising all of that would you begin to whisper about scars. There is an adjacent conceptual snare called superdeterminism, in which all the randomness we think we have is an illusion, because initial conditions conspired to correlate everything, including our choices of measurement settings, with the hidden variables that determine outcomes. In a simulation, superdeterminism is trivial to implement. You just write histories where apparent choices were never free. The problem is not logical, it is methodological. A theory that explains any pattern by referring to correlations fixed at the beginning is unfalsifiable unless it makes new, risky predictions we can test. As a research program, it stalls. In practice, device independence and cosmic setting choices are our best ways to quarantine the superdeterminist temptation and extract certifiable randomness that honors the spirit, if not the letter, of metaphysical freedom. Cryptography gives this topic teeth because we use randomness to secure secrets. If the universe delivered only pseudo-randomness controlled by the substrate, an operator with access to seeds could, in principle, read any code we write, predict any lottery we hold, and coordinate apparent coincidences at will. Two replies blunt the horror. First, if the motive mix. If we fear that our cryptography might be read by gods, we can at least do the work that makes it hard for mortals. Randomness is not a taunt. It is the background hum against which choice can be heard. Whether the hum is primal or computed, the music we play over it is still ours. Free will looks like a paradox, even before you add aliens, code, or controllers. We experience ourselves as choosing, hesitating, deliberating, committing, while living inside a rule-bound world where causes push effects in relentless chains. The simulation lens sharpens that tension rather than dissolving it. If the rules of our world are compiled somewhere else, if every interaction unfolds according to an engine's update laws, what room is there for real agency? Are we characters following scripts, or players with moves that matter? The question can get lost in metaphysics if we let it. A better route is to examine what kind of freedom we actually need for responsibility, meaning, and progress, and to ask whether a rule-bound, even deterministic reality can house it. The answer, if you are careful, is yes. Freedom on rails is still freedom, and sometimes rails are what make meaningful motion possible. Begin with a distinction that does most of the work: ultimacy versus authorship. Ultimacy is the fantasy of choices, uncaused by anything prior, uncaused causes erupting from nowhere. Authorship is the humbler power to act in ways that flow from who you are, your reasons, values, habits, and current grasp of the situation. Ultimacy is metaphysical and sterile. Authorship is psychological and civic. When we hold one another responsible, we do not ask whether a decision floated free of the universe. We ask whether the agent understood the stakes, could foresee consequences, could be moved by reasons and feedback, and was not coerced. Our institutions, law, education, friendship, aim to shape authorship. They succeed not by suspending physics, but by training systems like us to carry values forward through time and to revise those values under evidence. That is compatibilism with its sleeves rolled up, freedom as the capacity to act from internalized reasons within regular rules. If we are in a simulation, the rules are not threats to authorship, they are its conditions. A game with no rules is a fog. A world with no regularity offers no leverage for learning, no stable counters that connect action to outcome. It is precisely because the rules map causes to effects that an agent can plan, deliberate, and become accountable. You can predict that if you speak gently, a frightened child might calm. You can plan that, if you insulate a house, Energy bills will fall. You can commit to a friend, because in this world, commitments change behavior in reliable ways. Even if the substrate computes every micro-interaction in lockstep, the emergent fabric has enough stability for reasons to take root. Freedom on rails sounds like a contradiction, only if you think freedom requires floating above the track. If you think it requires being able to steer along it, it looks like adulthood. Chaos and chance complicate, but do not undermine that picture. A purely deterministic system can be chaotic. Tiny differences in initial conditions blow up into large divergences down the line. That undermines prediction without undermining law. In human terms, chaos supplies humility and possibility. When histories are contingent in this way, you cannot compress people to functions of a few parameters. You have to listen to their stories. You also cannot close futures off. Small, reason-guided acts can ramify through social networks and institutions in ways nobody can foresee. Indeterminism, quantum randomness, if it leaks into macroscopic processes, plays a similar role. Coin flips at the base do not give you ultimacy. They add noise that widens the distribution of outcomes. But neither chaos nor noise makes authorship less real. Reasons still compete inside a mind. Habits still bias choices. Commitments still shape paths. A rail line can split, and switches can be thrown by agents. Randomness can complicate where the car lands, but the hand on the switch is not an illusion. Counterfactuals are where freedom earns its keep. To ask whether you could have done otherwise is to ask whether, had certain upstream conditions been different, had you held a different belief, noticed a different feature, received a different argument, you would have acted differently. That is not a cosmic complaint, it is a practical one. It says, were you receptive to reasons that mattered? Could you have updated under better evidence? If yes, then could have done otherwise has all the content it needs. If no, if your mind is rigid, where it should be flexible, or brittle, where it should be resilient, then responsibility dims, and the task shifts toward reforming the agent or redesigning the environment. In a simulated world, the same standards apply. If the rules connect reasons to actions through learnable pathways, then counterfactuals make sense. If they don't, the world is unfit for agents. Choice architecture is a phrase from behavioral science that becomes metaphysics under ESH. Every shop layout, website flow, or policy default is a set of rails that tilt decisions without forcing them. Good design respects agency by making the good easy but not compulsory, and by making the bad possible but costly. If an alien operator wanted to study or encourage authorship, the world would be seeded with such architecture at every scale. Gravity punishes carelessness, scarcity punishes short-sightedness, social signaling punishes betrayal, empathy rewards cooperation. None of these are perfect, all are noisy. But the point is that the physics of bodies and the psychology of groups create incentives that convert reasons into outcomes. If you want agents to become authors, you give them a world where the grain runs in the same direction as the values you hope they can learn. Fairness yields durable peace, curiosity yields practical power, compassion yields resilient communities. Those correlations are not built into the universe by moral decree. They are engineered by selecting parameters and initial conditions that let them emerge. Script versus improvisation is another fruitful analogy. In a fixed script, the line you say at minute 40 was inevitable in a way that makes rehearsal meaningless. In improvisation, there are rules. Yes, and shared attention, commitment to the reality of the scene, but no one knows the next line. The emergent story is constrained by character, context, and the offers made by partners, yet it is not predetermined at the level that matters to participants. Agents are improvisers in a lawful scene. If a recorder were kept of the entire performance, a godlike spectator could say, it could not have gone otherwise, given the starting state and laws. That omniscient verdict does not rescind the participants' authorship. Their yeses and nos made the arc. Their reasons were not decorations pinned to motions already decided. We judge the improvisation by whether players listened, took care of one another, and made sense together, not by whether an external deity could simulate it. Moral luck often haunts this conversation. Two drivers drink. One arrives home without incident. The other, equally impaired, hits a pedestrian who darted out from between parked cars. We blame the second more, although the blame tracks outcomes with a heavy dose of luck. A simulation frame can bring clarity rather than fatalism here. Responsibility tracks the authorship that was under the agent's control, the decision to drink and drive, and luck tracks the world's uncontrollable contributions. A decent order distinguishes the moral assessment of choices from the legal and practical assessment of harms that need repair. You might build laws that assign strict liability for damages while preserving a moral vocabulary that criticizes the shared vice equally. That way, we clean up luck's debris without pretending authorship dissolves in it. Collective agency is where the rails can be bent, and a simulation built to test or teach would make this a recurring lesson. Individuals are narrow levers, institutions are long ones. We create organizations, laws, markets, and norms that compound small authorships into large moves. A ban on lead in gasoline changes the trajectories of millions of brains. A vaccine drive changes the phase portrait of a pandemic. A charter that empowers independent courts changes the incentives of those who would abuse power. If we were lab rats in a cage with a puzzle lock, the point would be to see whether we can build a culture that opens locks reliably. The rail metaphor becomes collective. We lay track toward futures we prefer, and the rules of the world determine whether the track holds weight or buckles under it. An alien researcher watching for authorship would measure not just individual choices, but the rate at which groups learn to align incentives with their better reasons. The spectre of manipulation lurks. If operators can tune environments, are our reasons our own? But environment dependence is not manipulation, it is life. Every choice is made somewhere, and somewhere always has cues and nudges. The ethical constraint for designers, aliens or humans, is to make the cues transparent and the nudges fair, to avoid traps that exploit cognitive deficits for private gain, and to construct arenas where minority voices can make offers others are required to hear. Freedom is not the absence of influence, it is the presence of influences that respect your potential to become a better chooser. A simulation that always sprung the worst temptations without offering countervailing scaffolds would be a rigged game. A world that offers ladders away from our vices and ramps toward our virtues remains a test of character rather than a machine for subjugation. There is also a hard problem of self-authorship. Can you change who you are by acting from who you are? Growth looks like a bootstrapping loop. You are impatient, you try to be patient, you fail, you reflect, you try again. At each step, the agent who acts is shaped by the one who acted before. The loop converges not by magic, but by scaffolding, practices, communities, and feedback that amplify small improvements instead of small relapses. A well-designed world supports such convergence. It offers gradients where effort pays off, communities where trust multiplies returns, and narrative resources that help agents reinterpret setbacks as information rather than as fate. That is pedagogy at the scale of a civilization. It is also the most intimate sense in which freedom grows real, by repeated authorship until reasons and habits line up. If we ever become operators of nested worlds, this act becomes instruction. Your job is to build rails that make authorship possible. Choose laws that make skill and care predictably matter. Choose ecological and social parameters that link cooperation to durable payoffs, punishment to proportionality, transparency to trust. Avoid worlds where a few early draws decide everything, because those crush counterfactuals and breed fatalism. Avoid worlds where noise dominates signal, because those drown reasons in chaos. Aim for worlds where reasons can be heard through the hum, where small moves compound into large civic arcs, and where people can become the kinds of authors who would make you glad you made them. And for us now, inside whatever this is, the prescription is plain. Treat freedom as the responsibility to cultivate reasons that are worth obeying. Invest in the practices, education, honest media, deliberative forums, fair courts, that turn authorship into a public good. Build institutions that let good reasons win without requiring saints. Accept that rails are real and insist that they be aligned with human dignity. Ask not whether your choices are uncaused, but whether they are yours, intelligible to you, responsive to evidence, and oriented toward goods you would defend in the open. If the operators are watching, that is what they will count. If no one is, that is still how freedom becomes more than a feeling. If someone is running a world like ours for reasons beyond spectacle, they are measuring. That is not cynicism, it is how learning happens. The trick is to infer from the inside what a morally serious operator would track, what dashboards would glow in the control room, and which dials would warn, intervene or shut down. Asking that question has a double payoff. It makes the simulation hypothesis concrete by turning motives into metrics. It also hands us a mirror. If those are the right things to measure from above, they are almost certainly the right things to measure from within. We can build our own dashboards, not because we imagine a score, but because steering any complex system requires instruments. Start with cooperation, the master variable under almost any motive. Cooperation is not holding hands. It is the reliable production of public goods in the shadow of defection. You can quantify it by looking at contribution rates to shared projects relative to opportunities for free riding, by measuring the cost we collectively pay to police cheaters, by tracking trust levels across groups and over time, and by watching how fast cooperative equilibria establish aftershocks. Proxy indicators include rates of contract enforcement without violence, levels of generalized trust reported in surveys aligned with behavioral measures, and the resilience of shared infrastructure when stressed. An operator would expect cooperation metrics to rise and stabilize as civilizations learn, then wobble under temptations and recover with institutional repair. A world that cannot lift or hold these numbers despite ample time is either badly designed or not ready. Alignment is cooperation's hard cousin, the degree to which power, human, institutional, artificial, stays tied to pro-social goals under distribution. Pressure. It has teeth when you measure who bears externalities and how quickly harms are internalized. You would track the ratio of private gains to social costs in dominant industries, the lag between scientific warnings and policy corrections, the prevalence of catastrophic externalities per unit of innovation, and the concentration of decision-making power relative to the diversity of those affected by its consequences. You would watch whether systems trained to optimize proxies generalize safely when the world shifts, and whether feedback loops exist that can rein in misaligned actors without violence. Alignment metrics are where Goodhart's law bites hardest. You avoid single numbers and insist on families of measures that cannot be gamed simultaneously. Transparency indices, whistleblower protection efficacy, audit rates, and the frequency with which institutions actually reverse decisions when shown evidence of harm. Sustainability sounds like a platitude until you instrument it. The physical economy flows energy and materials through a biosphere that obeys conservation laws. You measure energy return on energy invested, how much energy you get per unit spent, because low EROI systems tend to stress social fabrics. You measure material circularity, the fraction of inputs that are reused without downcycling. You measure distance to planetary boundaries, greenhouse gas concentrations relative to safe bands, biodiversity intactness relative to historical baselines, nitrogen and phosphorus flows, freshwater depletion, land system change. You do not track yearly totals alone. You track trajectories and variance, how quickly we move towards safety, how robust trends are to political cycles, how fragile supply chains are to single-point failures. A civilization that learns will bend curves early, spread risk, and build buffers. One that is merely competent will chase efficiencies until it hits walls. Innovation is not just rate, it is direction and distribution. A decent metric suite distinguishes between innovations that raise total factor productivity by squeezing labor, and those that expand human capability and reduce suffering. You would measure time to diffusion for health and welfare improving technologies across income deciles. You would measure the half-life of scientific consensus in fast-moving fields to track whether knowledge builds or churns. You would measure openness, what fraction of new knowledge is locked behind rent-seeking and what fraction is available for recombination. You would watch for premature optimization, systems that maximize narrow metrics at the expense of option value and exploratory capacity. An operator hoping to see flourishing would want a long tail of exploration alongside a healthy pipeline of exploitation, and would expect institutional designs, funding, IP regimes, education to balance the two. Resilience is the shape of recovery. You measure mean time to recovery after shocks across domains, public health after outbreaks, credit systems after liquidity crunches, ecosystems after fires, trust after scandals. You measure modularity and redundancy. How many components can fail before a function collapses? How easily modules can be reconfigured to bypass damage? You watch for rigidity traps, where systems become so optimized that small perturbations cause catastrophic collapse. You measure slack deliberately and celebrate it, where it buys anti-fragility. On the social side, you track participation breadth in crisis response, because wide engagement correlates with both speed and legitimacy. A world that keeps cutting every buffer to optimize will impress an operator with short-term performance and then fail their long-term test. Justice is not a garnish. If outcomes are systematically detached from desert, if effort and honesty buy little while extraction and deception buy security, learning stops. You measure inequality not as a single Gini coefficient, but as a set of lenses. Wealth concentration at the top, floor quality at the bottom, intergenerational mobility over multiple cohorts, and the rate at which positional goods crowd out universal goods. You track procedural justice, the likelihood that similar cases receive similar treatment independent of identity, the cost in time and money to access the protections of law, the correlation between political voice and material interest. You measure repair, how quickly and adequately harms are acknowledged and remedied. An operator measuring justice is not hunting for utopia. They are looking for gradients that point toward reciprocity and away from predation. Culture resists meters and yet must be metered. You track cultural diversity and the persistence of minority traditions under majority power, not because novelty is intrinsically good, but because monocultures are brittle. You measure the balance of narrative frames in media ecosystems, how often zero-sum frames dominate over positive-sum, how often outgroup threat is used to mobilize compared to shared challenge. You measure the ecology of attention, how much of civic bandwidth is consumed by outrage cycles versus deliberation, how quickly falsehoods are corrected and by whom, how often public discourse produces policy-relevant synthesis rather than identity performance. These are messy, but they matter because meaning is the medium through which all the other variables flow. Education is the factory for authorship and cooperation. You measure not test scores alone, but transfer, the degree to which people can apply learning outside its original context. You measure epistemic humility and curiosity, admittedly by proxies like willingness to update beliefs under evidence, comfort with uncertainty, and participation in cross-ideology dialogue. You measure civic skill, knowledge of institutions, practice in deliberation, and experience with service. You measure fairness in access to those goods. An operator measuring education wants to see a pipeline that turns raw cognitive horsepower into wise agents who can navigate complexity and resist manipulation. Health threads everything. You track life expectancy and healthy life years. Yes, but you also track mental health, loneliness, addiction, and despair. You measure how much health variance is explained by zip code and income. You measure the latency between knowledge and access, how long it takes for a new therapy to reach the poorest quartile. You measure the ratio of preventive to reactive spending. A healthy population thinks better, cooperates more easily, and absorbs shocks with less panic. World designers who neglect health are not serious. Inhabitants who treat health as private luck will find their other metrics mysteriously slide. Governance is where all these strands are braided. You measure rule of law robustness, corruption levels under audits that are hard to dodge, turnover without violence, policy responsiveness to evidence versus to donor pressure, and the degree to which institutional failures are corrected by reform rather than by revolution. You instrument checks and balances with stress tests. Can a demagogue capture the apparatus? Can a minority veto block all change? Can bureaucratic inertia stall urgent action? Can emergency powers be ratcheted down after danger passes? A world that learns will design for graceful failure and reversible decisions. An operator who cares will watch whether we do. Now the simultaneity problem. None of these metrics can be maximized alone without perverse effects. Try to maximize innovation, and you can burn resilience. Try to maximize resilience, and you can strangle innovation. Try to maximize equality, and you can starve incentives. Try to maximize incentives, and you can entrench dynasties. The right picture is a Pareto frontier, a curved ridge of best trade-offs given constraints, and the right program is to push that frontier outward by institutional imagination and technological progress. A smart dashboard makes trade-offs visible, refuses single scores, and highlights when improvements in one dimension are bought by hidden degradations in another. Goodhart's law is not a curse if you expect it, and design around it with rotating indicators, adversarial audits, and a culture that treats metrics as conversation starters rather than as gods. How would an operator avoid biasing measurement itself? By committing to pre-declared metrics, by separating observer roles from designer roles, by using blinded analyses where possible, and by inviting adversarial evaluation, other polities at the operator level, checking your definitions and your numbers. From inside, the analog is independent statistics offices, pre-registered studies, open data, and media ecosystems that reward corrections. If a dashboard can be cooked without being caught, it will be. The cure is socio-technical, process as much as principle. If the operators are educators, their dashboard also includes learning curves. They would track how quickly we discover basic invariants, physics, how quickly we discover better ways to cooperate, institutions, and how often we transmit those discoveries intact across generations, culture. Plateaus are expected, regressions happen. What matters is the area under the curve and the slope after a stumble. That means measuring institutional memory. How often do we repeat mistakes? How do we embed hard-won lessons into defaults? How much of our progress depends on a few heroes versus a durable fabric that survives them? It also means measuring moral circle expansion. Who counts as us this century compared to the last? And what rights attend that counting? There will be temptations to add a score. Don't. Scores incite leaderboard thinking and invite trickery. Dashboards resist it by stubbornly staying plural. They tell you, insistently, that a civilization is a bundle of tensions and that maturity is learning to manage them. If there are operators, they will resist scoring for the same reasons we should, because the habits that produce real gains are more important than the snapshot. Finally, turn the mirror fully around. We do not need aliens to build instruments for stewardship. We can track cooperation by how we fund and protect goods no one owns. We can track alignment by how quickly we correct harms that make someone money. We can track sustainability by whether our kids inherit options rather than debts. We can track innovation by how often we make the useful beautiful and the beautiful useful. We can track resilience by how gracefully we fail. We can track justice by whether the floor rises and the ceiling decalcifies. We can, if we choose, commit to pre-registering our grand experiments, sharing our nulls, and letting critics into the room before we act. If someone is watching, this will look like signal. If no one is, it will still be the only reliable path in a world this complex. Either way, the right metrics are not about being judged. They are about becoming the kind of civilization that does not need a judge to do what is right. Every few years, the universe seems to lean down and whisper, and every few years we learn, we mostly heard ourselves. Fourth wall breaks, moments when reality looks like it's winking at the audience, are catnip for a simulation lens. Prime numbers allegedly sketched into the sky. A lone radio shout that looks too clean to be nature. Millisecond flashes, here, gone, here again, from galaxies unimaginably far away. If there were operators, and if they were the sort who enjoyed an inside joke, these are exactly the sorts of places you might expect a sly ping. But the closer you get to the data, the more those winks resolve into eye floaters, quirks of instruments, artifacts of analysis, or the inevitable weirdness you get when you stare at noisy, gigantic systems with a million degrees of freedom and a mind that hates coincidence. Taking the alien video game frame seriously does not mean treating every anomaly as a patch note. It means asking what a genuine fourth wall break would have to look like to survive our best boring explanations, and then admitting that almost none of the candidates meet that bar. The cosmic microwave background is an obvious canvas for people who want to find messages. It is everywhere. It comes from everywhere. It encodes the earliest conditions we can see with light. If an operator wanted to watermark the run, the argument goes, what better way than a faint structure at the largest angular scales, something any cosmology-capable species will eventually map? Over the last 2 decades, several large-scale oddities have been argued over. The unexpectedly low power in the quadrupole, curious alignments between the quadrupole and octopole dubbed the axis of evil, hints of a hemispherical power asymmetry, a cold spot whose profile looks, in some analyses, stranger than Gaussian fluctuation would prefer. None of these are prime numbers carved across the firmament. They are statistical textures whose surprise depends on how you slice the data and how you count surprise after looking. Each of them draws sober counter-narratives, foreground contamination from our own galaxy that is hard to model perfectly, instrumental systematics that leak scan strategies into the map. The fact that if you compute enough summary statistics on a high-dimensional field and selectively report the ones that look weird, weird will look common. The right lesson for a simulation realist is methodological. Define your test before you peak. Otherwise, every anomaly feels like a wink because you're drawing the eyes after the smudge appears. The prime numbers in the sky meme is even easier to deflate. To encode a recognizable sequence in a cosmic map, you need a convention for where the message starts, which basis to read it in, how to handle noise and masking, and what units count as a bit. Humans can agree on those conventions because we make them together. A universal message has to survive species that do not share our geometry, our pixelization schemes, our penchant for spherical harmonics, or our taste for base 10. The more robust you make the coding, the more energy you need to lift it above noise, and the more you risk breaking the laws you meant to respect. An operator obsessed with subtlety would not graffiti the sky with primes. An operator obsessed with communication would not choose the noisiest, most path-dependent billboard available. The fact that cosmologists keep finding anomalies and then beating them down with better calibrations is not proof of a careful redactor. It is proof that turning a faint fossil glow into a map of the early universe is devilishly hard. The wow signal of 1977 carries a different emotional charge because it looks like Hollywood. A narrowband radio spike in the right region of the spectrum, strong enough to be striking, long enough to be interesting, never to be seen again from the same patch of sky. It has been a Rorschach test for 40+ years. To the credulous, it is a greeting. To the dismissive, an uninteresting blip. The honest middle is an intriguing one-off that never congealed into evidence because follow-up saw nothing, and the original setup lacked the redundancy to rule out all prosaic causes. If we were inside a game and the operators wanted to poke us, a single, unreplicated tone that our best practice cannot verify is a poor choice. They would know our verification culture craves repeatability. The more interesting reading is sociological. The wow signal taught a generation how to chase anomalies without marrying them, how to build systems that record all the context you'll wish you had later, how to treat an eyebrow raiser as an invitation to instrument the sky better rather than as a story you now owe belief. Fast radio bursts arrived as if scripted for our era. Surprise, skepticism, then a flood. Millisecond-scale flashes from cosmological distances, apparently coherent, initially so odd that many suspected interference or analysis error. Then more were found, in other telescopes and other backends, and a few began to repeat. Catalogues grew, host galaxies were identified, propagation effects turned FRBs into tools for weighing the cosmic inventory of electrons. For a while, the regularity of one repeater's spacing fueled breathless lighthouse or beacon metaphors. But repeating does not mean intentional, and regularity does not mean coded. Nature makes clocks, magnetars with crustquakes, orbital resonances, plasmas with their own self-organizing dynamics. If you want to claim admin ping, you must rule out the full zoo of high-energy astrophysical engines. FRBs are, today, a frontier in that old, satisfying style. Weird things we didn't expect that turn out to be physics, and that turn into rulers for other physics once you calm down enough to stop demanding a narrative. The temptation to treat cosmic rays at the highest energies as grid tellers, arrows pointing through the lattice of a discretized world, has the same basic problem. If you only search for anisotropy after you have binned and filtered and massaged the data a dozen ways, you will be able to extract a direction every time. If you write down, before you look, what anisotropy you would count, at what energies, with what cross-calibration between instruments, and then you publish your analysis code and pre-commit to your stopping rules, the sky almost always shrugs. The tails of any distribution are where oddness lives by definition. A simulation frame that respects science has to take its own medicine, define the test, share the data, accept nulls, and stop dragging every curious tale back to the throne of a storyteller. Even in the rare cases where an anomaly survives first contact with better data, nothing about looks weird picks out operator intervention. The cosmos is a multi-scale, non-linear, chaotic system. It manufactures low-probability events by the billions. Our lives are too short to sample even a sliver of its repertoire, so our priors are terrible. Early time phase transitions can leave imprints that look like dirty fingerprints. Quantum fluctuations blown up by inflation can seed structures that, from our one vantage, look aligned when they are not. Selection effects in what regions of sky we survey, with what sensitivity can leave lattice-like maps of supposed messages that are in fact mosaics of our attention. A genuine fourth wall break would have to clear a brutal bar. It would need to be pre-registered in a way that could not have been tailored to the data after the fact. It would need to repeat under independent instruments with independent pipelines. It would need to encode content that resists every native explanation without resorting to fine-tuned special pleading. And it would need to arrive in a language no natural process plausibly speaks. Almost nothing we've loved in the anomaly genre comes close. That bar is not set high to protect a worldview. It's set high to protect us from ourselves. The human brain was built to compress and to survive. It stitches patterns out of noise, because sometimes there is a tiger behind the leaves, and missing one is more expensive than jumping at shadows. Transplanted into cosmology and high-energy astrophysics, that bias turns into elaborate folk tales that feel rigorous because they wear math. The simulation hypothesis, improperly handled, supercharges the bias by providing a ready-made author for any coincidence. If you are trying to do honest work inside this frame, you must develop an allergy to apophenia. You must like null results, because a civilization that can like nulls can learn. There is another reason not to fetishize possible winks. They distract from the quieter, deeper, fourth wall breaks we already live with. The fact that mathematics written in the language of symmetry and invariance matches the world so well that we can predict the outcome of a particle collision to many decimal places. The fact that information seems to have a thermodynamic price and that there are limits, visible to us, on how fast any process can evolve or how much memory any region can hold. The way renormalization links micro to macro and lets simple laws generate complex textures. These are the places where, if you were looking for a signature of design in the broad, you would lodge your admiration. They are not jokes, they are not winks, they are the sort of elegant economy that any decent engineer would chase. If there is a fourth wall, it is already broken in the way the rulebook's compactness propagates across everything we do. Turning away from that to chase a prime scribbled across the CMB is like ignoring a cathedral to scan for graffiti in the mortar. Finally, there is the ethical undertow. A culture hungry for signs is a culture that can be manipulated, and a politics that builds power on "we have seen the pattern" is a politics that becomes allergic to correction. If you bring the simulation lens into public, you owe it a chastity belt. Do not feed it with rumors. Do not inflate ambiguous signals into meaning. Do not promise revelations if only the faithful keep the faith. Treat anomalies as teachers of humility, not as rewards for the initiated. The most dignified way to live under a hypothetical audience is to behave as if they respect discipline more than spectacle. If they do not exist, that posture still saves you from 100 swamps. So yes, let the world surprise you. Just refuse to be easy to fool. Ask of every apparent wink whether it can carry the weight of pre-registered prediction, whether it repeats under new eyes, whether it has content that refuses to be naturalized. Expect the answer to be no. Keep building instruments that will make you honest the next time you want a story. And if someday something survives all of that, it will not need you to defend it with rhetoric. It will stand, and then we can talk about what it means to be waved at by the world. Why don't we just ask them, is the most human sentence in this whole topic. If there are operators, researchers, educators, curators, artists, safety engineers, why not send a message up and see if anyone answers? The urge is understandable. It promises closure, a shortcut through epistemic fog, an end to the long discipline of inference. It also carries every kind of hazard, scientific, ethical, sociological, even existential in the sober, not cinematic sense. The act of trying to talk to hypothetical operators is not just a radio transmission. It is a cultural choice with downstream consequences, whether or not anyone is listening. The right analysis has to weigh what we could gain against what we risk and what we might irreversibly deform in ourselves by making the question itself central. Begin with the most basic choke point, testability. Any scheme to contact the devs is a hypothesis test in disguise. You choose a channel, craft a message, define what counts as a reply, set a window, and plan your analysis. In the absence of all that, you are setting up a machine to find patterns in coincidence. The universe is big. Improbabilities happen constantly somewhere. People are good at cherry-picking and at retrofitting intent onto noise. If you want to be serious, you have to do what sober SETI advocates have learned to do: pre-register the protocol, publish it, recruit adversarial collaborators who think your plan is silly, and give them veto points over the definition of acknowledgement. You have to run blind to your own hopes, and even then, an apparent answer would be one of the hardest claims to defend cleanly, because any real reply would be designed to hide from precisely the kinds of tests you are running in order to protect the run's integrity. The basic geometry of the problem is perverse. The more cautious and decent the operators are, the less your tests can possibly succeed. Next comes channel choice. Radio is democratic from our standpoint. It leaks easily into the sky. Instruments are cheap, and the math is friendly. If you imagine an outer layer that can see in, however, you do not know what they can monitor without stepping on our laws. A decent operator would avoid channels that require breaking conservation or locality to listen. They would avoid intervening at all unless a red line is crossed. They would not need your message to know you exist. They wrote the initial conditions. They would not need your arguments to guess what you want. A library of runs longer than our history would make us predictable in broad outline. The case for talk has to rest on something other than an information bottleneck. It usually rests quietly on a plea for attention or mercy. Those are not scientific queries, they are prayers. If you want to pray, be honest about it, and be prepared for silence that does not, either way, vindicate or refute your cosmology. The ethical risks are not out there, they are in here. Announcing that you are addressing the operators creates a coordination point for charlatans and fanatics. It incentivizes people to stage miracles, to weaponize coincidence, to build cults around alleged replies, to bypass the slow, plural deliberation of ordinary politics by invoking a higher court. It tempts governments to regulate speech nominally to prevent provocations, or to seize the mantle of official intercessor. It tempts lonely people to reorganize their lives around a promise no one can keep. If you think this is pessimistic, recall that human societies do this with much flimsier hooks than we are in a sim. A responsible community does not hand demagogues a new lever. There are subtler hazards whose names do not end in catastrophe. One is moral licensing. If you come to believe that benevolent operators are watching, you may risk more, care less about tail risks, or plead helplessness in the face of structural injustices because they wouldn't let the worst happen. Another is fatalism. If you come to believe that indifferent or cruel operators are running you for amusement or for science, you may excuse apathy or malice as the only sane response. Both are corrosive to the civic habits that make us less dangerous to one another. The simulation lens, handled well, should motivate humility and responsibility. Handled badly, an attempted dialogue with imagined custodians flips it toward abdication. Suppose, despite all that, you still want to try. What could a non-reckless hello look like? It would have to be informationally modest, ethically scrupulous, and scientifically sterile. That is, it cannot be allowed to produce a false positive that reorders the culture. One option is to embed the gesture in art and ritual, where it cannot hijack claims about nature. You let poets and composers make operator pieces that encode our best hopes and failures, and you do not call them experiments. Another option is to wrap any technical attempt inside guardrails designed to defeat drama. Messages transmitted only within tiny bands at pre-declared times. Acknowledgements defined so conservatively that almost nothing clears the bar. Result: announcements embargoed until adversaries concur. Licenses to run the protocol limited in number and duration. The point is not to smuggle science past a skeptical priesthood. It is to avoid adding yet another attractor for magical thinking. What would we say is a thorny question, only if you imagine you might change their minds. There is no argument we can write that a civilization with star-scale engineering has not already seen. There is no ethical insight we can pen that would be novel to beings with libraries of runs. What might be meaningful, if anyone is watching, and if meaning flows upward at all, is not content but texture. The demonstration that we can do difficult things together without lying to ourselves. A message that says, we pre-registered this, we invited our critics, we promised to call even an interesting blip a null unless they agreed, and we kept our promise, teaches more about us than any clever math puzzle. It says we can be trusted with power, because we can be trusted to restrain our appetite for wonder when restraint is due. There is a popular alternative: do nothing special and let our best work stand as our address. That is not resignation. It is, arguably, the most legible introduction we could make. If there are operators with dashboards, the channels they watch are already open, curves bending in the direction of sustainability, cooperation that holds under stress, institutions that can reform without blood, technological progress that spreads benefits without concentrating harms, rights expanding to include those without force, curiosity that is disciplined, not credulous, art that makes strangers legible to one another. The way to speak to anyone worth speaking to, above or beside us, is to make those graphs move. A sim run is not a college admissions essay. You do not persuade with a page, you persuade with a life. There remains a small set of research moves that look like proto-contact, but are in fact just good science. You can design experiments that probe the seams of law, tests of Lorentz invariance, constancy of constants, device-independent randomness, because those would be the first, faint places an implementation detail might leak if one were going to. You can pre-register what would count, and you can enforce a culture that loves nulls. If anything ever survives that gauntlet, it will be worth talking about without the help of a myth. Until then, talking to the operators is at best a metaphor for building institutions that deserve trust, and at worst, a hazard to be contained. There is also a dignity argument for silence that has nothing to do with fear. If we are subjects in someone else's study, then there are norms about participants trying to manipulate the investigators. We bristle, and rightly, when subjects in our own experiments attempt to hack demand characteristics, guessing the hypothesis, and acting to confirm or confound it. We want authentic behavior under the conditions we set, because that is how we learn. If we think we are being measured on our capacity for coordination, patience, and fairness under uncertainty, then the most adult way to answer is to show those things without bargaining for extra credit. The fourth wall, if it exists, is there to protect the meaning of our acts. A final pragmatic consideration clinches it. Projects that center the operator hypothesis will attract a skewed coalition: the credulous, the performative, the opportunistic. You do not need to demonize those personalities to see the organizational risk. Coalitions like that are volatile, and volatile coalitions leave behind disillusioned people who will not next time show up for the slow work that actually changes lives. If you care about steering a civilization through bottlenecks, you husband attention like a scarce resource. You spend it where the payoff is robust across cosmologies, on public health, on education that teaches people how to know when they do not know, on energy systems that lift without poisoning, on media that accelerates correction rather than amplification, on courts that treat like cases alike, on science that cleans its own house in public. None of this is a plea to stop imagining. Speculation is how we stretch our models and rehearse our ethics. But imagination should widen the field of responsible action, not narrow it to a theatre with an audience we cannot see. If there are operators who can hear us, they already do. If there are not, we have each other, which is both less and more than the fantasy promises. Less, because no one is coming. More, because it means that every decent thing that happens will be something we chose to build. In that light, talking to the devs has an answer after all. Talk to your neighbors and build systems that make talking to your neighbors easier. It is the only message we can send that doubles as a life worth living if no reply ever comes. If you were trying to make a world that feels continuous while paying only for the parts anyone actually touches, you'd build something that looks suspiciously like quantum mechanics. Superposition is lazy evaluation. The world carries forward compact amplitudes, possibilities, until an interaction forces a commit. Entanglement is shared state without chatty messaging. Correlate subsystems at creation, let them separate, and you can guarantee matched outcomes at red time without blowing your bandwidth budget in between. Decoherence is garbage collection for unrealized branches. Once the environment has irreversibly recorded which way something went, the other amplitudes aren't destroyed so much as rendered unaddressable for any practical agent inside the system. No signaling theorems are the concurrency rules that keep this all sane. Correlations can be spooky, but they never become a wire you can use to shout faster than light, which is exactly how you stop eager processes from breaking causality. Even the path integral picture has an engineer's smell. You could compute exact micro-trajectories, or you could let every path vote with a phase and watch destructive interference cancel the waste. What survives are stationary phase contributions, the extremal, summary behaviors that just happen to be the pieces classical agents can track. On finite budgets, that's the compression you want. Let the math do the pruning, so you don't render every pixel of every counterfactual universe. Quantum limits look like service quotas. The Heisenberg relations put a floor under what joint questions you're allowed to ask at once, which is how you prevent a clever user from pinning down too many conjugate facts and forcing the engine to spill internal state. The Margulis-Levitin bound and Landauer's principle are rate cards. How fast coherent evolution can go per unit energy, how much heat you must pay to erase. Black hole entropy and the holographic bound read like capacity planning. If you try to stuff more information into a region than its area allows, you don't get a higher res world. You get a different object with different bookkeeping. None of that proves an outer layer. It explains why the alien video game lens keeps finding traction at exactly the seams where physics feels both elegant and thrifty. Inside the rules, the bus still hurts, love still changes you, and choices still cost. But the rules themselves carry the vibe of a system that refuses to pay for detail no agent can reach, that enforces invariance to keep eons consistent, and that hides its scaffolding behind symmetries so players can't see the stagehands. If the point of this run is to see what we do with reliable constraints and generative uncertainty, quantum weirdness is the perfect mix. Enough slack to make novelty real, enough structure to make responsibility possible. If the simulation idea has teeth, it also has fangs. One bite is nihilism. If this is just a game, why bother? Another is fanaticism. If there are operators, someone will claim to speak for them. A third is moral offloading. If outcomes are graded elsewhere, we can skip the hard work here. Each is a failure of nerve disguised as insight. The antidote is to fix the locus of meaning where it always belonged, inside relations, projects, promises, and to keep our standards of evidence higher than our appetite for wonder. Nihilism melts if you stare at it with the right eyes. Every good you've ever touched, care that eased pain, craft that made a tool sing, knowledge that let strangers coordinate, was made inside constraints. Whether the constraints come from base physics or an engine's rulebook is a difference with no practical distinction. You still wake into a world where actions propagate through real bodies and institutions. You still inherit debts you didn't choose and options your predecessors bought. You still get to raise the floor for whoever comes next. If only simulated can cheapen that, then so could only atoms, and it doesn't. Fanaticism thrives on ambiguity and attention. The cure is procedural humility. Pre-register the claims you're willing to believe. Submit them to adversaries before you submit them to audiences. Reward correction over charisma. A culture that treats error bars as badges of honor is inoculated against priest-kings of the substrate. Build institutions that make it costly to claim secret channels. Open data, independent replication, laws that punish fraud, and media that feature retractions as prominently as scoops. If there are operators worth talking to, they will recognize that posture as maturity. If there aren't, you've still made a saner public square. Moral offloading collapses once you refuse magical guarantees. No outside rescue is coming to fix climate, clean water, antibiotics, bias, or bombs. That's not bleak, it's clarifying. Responsibility becomes local and contagious. Your lab's data hygiene, your city's floodplain maps, your company's externalities, your parliament's emergency powers, ethics scales by imitation and infrastructure. We do the next correct thing at human scale and make that the default for whoever follows. If an audience exists, that's the signal they're watching for. If none does, it's still the only way a precarious species gets sturdy. There are softer hazards: apophenia, apathy, aestheticism without care. The treatment is the same triad we've been circling: discipline in belief, mercy in design, courage in action. Discipline keeps us from mistaking vibes for laws. Mercy keeps us from building hells in code or policy. Courage keeps us from waiting for permission to do what we already know is right. So we hold two thoughts without letting either eat the other. The world may be implemented, our duties are not. The rules may be thrifty, our generosity must not be. We will end with the plainest takeaways: how to live well under reliable constraints and generative uncertainty, then close the curtain with whatever dignity we've earned.